Gentlemen, welcome to the 2024 Principles of Secure Compilation workshop. Our wonderful program committee has accepted 11 papers for your entertainment today. And so I'd like you please to give a big round of applause to our 22 program committee members who worked hard for you today. So thanks to those of you who are here and to those of you that are at home. So thanks, PC. So let's start right in with today's keynote, which is given by Peter Sewell, whose third-person bio I haven't learned by heart. You weren't supposed to see this, but well. Peter Sewell is a professor of computer science at the University of Cambridge. Well, if I have to stop, then let me just say he's going to give a very interesting talk. And in the interest of time, please, Peter, the floor is yours. The laptop is also yours for the remaining hour.
Thank you. Thank you for the invitation. Thank you for coming here at the end of a long week in POPL. So this is going to be a very short talk. Can we reason about the security of concurrent systems code? No. More specifically, can we reason that a hypervisor provides its intended protection properties? No. More specifically, can we prove that a production industry hypervisor provides its intended protection properties? Yeah, this is not getting any easier. Could we prove that a really specific production industry hypervisor provides its intended protection properties? For example, PKVM. What is PKVM? A protected KVM is a hypervisor that Google has been building for the last couple of years and still is with a bunch of people in King's Cross, not very far from here. The idea is that this will protect the Android kernel and other critical components from compromises, especially kernel compromises, after boot. Kernel compromises are not that uncommon, so people really care about this. And moreover, they want to do this in a way which pragmatically can be deployed to all of Android, not just Android on Pixel and so forth. Right? Some of this is already running in some of your phones. Can we do that? This is still not getting any easier. This is getting harder. Can we do that for real? What do I mean by for real? Well, one thing we could do for real would be to write nice papers about it. That's pretty real. But, well, it would be nice to actually verify the binary that runs above the architecture spec that it runs on. The architecture spec is like all of ARM-A with its ISA and its concurrency and address translation and everything. It'd be nice to verify the binary that the Google devs off in their office near King's Cross are actually producing, which is built using C and embedded assembly and Clang and lots of tools, which they are not going to change. Arguing that those people should switch to use Concert, for example, that's a non-starter. Can we prove the thing in a way that actually works with the conventional engineering that those people are already doing and are going to keep on doing whatever we do? Well, that would be nice. Can we maintain the thing without infinite expense and a terrible challenge of keeping our research community doing proof maintenance for 20 years into the future? Ooh, that would be nice. Oh, can we do any of that without an insane amount of effort? Clearly, no. Well, definitely no today, but what I want to argue in this talk is this is not out of reach, and it is an excellent focus for research, and the potential payoff very large. Right? So in this talk, I'm going to talk about some of the challenges and some of where we are now, and I've wibble about some of the open problems, and maybe inspire people to think about the open problems, because there are lots of spare open problems. We're not short of problems here. So we, who is we? We is a lot of people who are more or less involved in a sort of informal project that we've had for the last couple of years to kind of poke at this problem in various ways. So there's a bunch of people in Cambridge, quite a few of them here, and some of our colleagues in Aarhus and in MPI-SWS and in Edinburgh and in Radboud and in SNU. All these people on the left-hand side are kind of on the verification side. And then these people on the right-hand side, who are much more important than us, are actually building the hypervisor in Google and supporting this verification activity and so on. Yeah? So there's a lot of people. None of these people are working full-time to verify PKVM, but they've all done or are doing, or both, some pieces of this problem, or some things that we think we can fit together. We hope we can fit together. So I have to tell you a little bit about PKVM. And I have to tell you a little bit about ARM. Right? So some of you will already know ARM provides sort of a hierarchy of exception levels, and more privileged code runs at a higher numbered exception level. So there's an EL2 where hypervisors like PKVM run, and then EL1 where the Android Linux kernel runs, and then the rest of Android and applications and so on run at EL0 above that. And in a PKVM system, you might have the Linux kernel encapsulated by this hypervisor, and also other virtual machines, maybe some of them also running copies of the Linux kernel, protected from each other. What's the code like? So, yeah, this is not written for verification. This is written as a bunch of C and ARM assembly code as part of the Android Linux code base. So it's Linux kernel code. It uses a bunch of Linux kernel headers, uses their coding style, all of that kind of stuff we can't change. I have to tell you something about ARM. So how does a hypervisor work? It isolates things using address translation. So ARM, well, it supports lots of different kinds of regime, but in the one that we're using here, there's a stage 1 address translation, which takes virtual addresses and maps them to intermediate physical addresses, and normally this is controlled by EL1 operating systems. And then there's a stage 2 that maps intermediate physical addresses to real physical addresses, and in this case, those are controlled by the hypervisor. So during boot, the Linux kernel, which these people call the host, hands over control to PKVM. So the kernel is trusted for the initial part of boot, but not after that. And then PKVM makes up a mapping for its own execution and a stage 2 mapping within which the host runs, and a stage 2 mapping for each virtual machine. And basically what it does is make sure that the ranges of those mappings are mostly disjoint. Right? That's where security comes from. Yeah. And then after that, the host isn't trusted, the guests aren't trusted, but PKVM gives a little API via hypervisor calls, which are exceptions up to EL2, to share pages and donate pages and start new VMs and that kind of thing. Right? So not a very big interface. Okay, so we're going to talk about the challenges. There are lots of challenges. And we're going to do that until I run out of time. It's not a very big audience. If people are mad keen to interrupt, maybe we can interrupt during the talk. Imposing a load on Marco to run around with a microphone. Is that okay?
Gladly.
It's fine. So, first challenge, what is the underlying ARM semantics anyway? So ARM will give you, on their web page, at the moment, 12,940 pages of prose and pseudocode. That's the spec. That is obviously not totally tractable in that form. So we need, an honest mathematical definition of the envelope of architecture allowed behavior. So there are several aspects to nailing that down. Right? So the first is the sequential stuff. What is the sequential ISA? Or really the instruction local ISA? And that is kind of nailed down, right? So about 10 years ago, Alistair Reid, then inside ARM, shifted them from a purely pen and paper pseudocode to a not entirely mathematical, but machine processed pseudocode. And a few years later, we, working with him, took that and translated it into our SAIL ISA definition language, which is a bit more strongly typed and more convenient in other ways. And from that, we generate theorem prover definitions and executable emulators and relaxed memory tools and what have you. Mm-hmm. And recently, where we is Thomas? Where's Thomas? Thomas, excuse me. Thomas and Brian have updated this to the current version of the ARM assay, so ARM 9.4a.
That was not executable.
The ASL is within ARM is sort of executable, and this, you compile it to C, it's sort of executable. Right? So for a previous version, we is Brian and Alistair, ran the ARM internal architecture conformance tests on that C emulator, and you can't say they were perfect, but they were about as perfect as the results that ARM get. One thing you have to understand, nothing here is perfect. Right? You can say, oh, we would love a foundational proof of everything, but you have to understand that, this is not perfect either. You have to kind of balance the effort and the reward. Okay, so this is fine, but it's a teensy bit big. Right, so, and it gets bigger rather disturbingly fast. So 9.4a, Brian tells me, is 420,000 non-white space lines of spec. Okay, that's not huge by software standards. It's a bit big. So that is massively larger than the hypervisor. Right? The hypervisor boils down to about 20 or 30,000 ARM instructions. Kathleen?
Did you get input from ARM also in this newer version, or did you try to reconstruct yourself how the changes were?
They give us, so these days, they provide quite a lot of this publicly. Actually, here we take sort of some of their public, we take something which is equivalent to the thing they do publicly and some stuff that they give us just secretly, and we can glom those into SAIL, and then we are allowed, with an agreement with them, to publish the resulting SAIL model under a usable license. Okay. I don't think we've attempted to revalidate this version. Maybe one day we should do that when we have spare time. Ho, ho, ho. Okay. So that's good. And that's kind of everything you might think of. All the instructions, all the exception levels, the translation walks, the debug architecture, all the ISA stuff. That's good. It's great. Why is it 400 and whatever, 100,000 lines? Well, some of you might have seen these slides before. If you just think of one simple instruction, add 1 to the value in that register and put it in that register, then in a nice, easy semantic model, you might write down its semantics as just that. It seems perfectly sensible. But really, that instruction is inside the spec a whole family of add and subtract instructions. And this is actually more or less the complete semantics for that instruction for real. So you have to decode the bit pattern, because this is a machine code semantics, and then you have to decode it some more. And then you have to run it, and this is like parametric on whether you're doing add or subtract or whatever. And inside here, you're accessing some registers. And some of that's kind of straightforward, but this instruction also can apply to the stack pointer. And the stack pointer is a banked set of registers. So at different exception levels, it's a different register, right? So that's indirected via some auxiliary functions. And then you have to read some system registers to know which exception level you're at in order to know which register to access, and so on. And then at the end of the day, you have to actually compute some flag bits and do some honest-to-goodness arithmetic. Right? So none of that is rocket science. There's just a lot of it. And this is the example that fits on a slide. Okay. This is a register-only instruction. The instructions that touch memory are much more fun. So there's a whole hierarchy of auxiliary functions that, for example, do a memory access at some address. And that might be a big memory access. It might need to be chopped up into smaller ones, which are single copy atomic. So this calls this on a bunch of sub-accesses. And then this mem single takes a virtual address, and it will do some work, and then eventually call what you might think of as a primitive effect as a physical memory read. Okay? So there's a hierarchy of functions in the spec that do that. What happens between here and here is address translation. Well, we care about how address translation works and what it means, so let's have a look at that. So there's a hierarchy of functions to translate a virtual address, and that uses full translate, and that does first this stage 1 translate, which involves, in the ASL, a page table walk reading memory a bunch of times, and each of these accesses are with respect to an intermediate physical address, well, if they're host or guest accesses. So then you have the same kind of deal, translating from intermediate addresses to physical addresses, and each of those might have to read memory a bunch of times. And the first accesses are translated by the stage 2 translate 2. So you have to read memory a lot. And this is, in any specific context, this is not super complicated, but then there are, umpteen different configurations of everything, which make it extremely complicated. But we know what it is, because they tell us. It's good. Okay, so we kind of know what the sequential instruction local semantics is, but we know that ARM is not a nice, simple SC machine. Right? ARM has a relaxed memory model. So we need to figure out what that is. And some of that, we and other people have figured out over the years, and there are these relaxed memory models in different forms and with a lot of different litmus tests illustrating particular relaxed behavior for the user mode concurrency. I say user mode, it's not really EL0, it's all the things that don't involve features that you can't do at EL0, like exceptions and address translation and instruction cache maintenance. You can do a little bit of that. And so on. Right? So this was really only the merest beginning of understanding what the underlying relaxed semantics is of the platform that we're building above. Right? Because you need, to talk about a hypervisor, you need to know how all of these things work. Right? So for the last couple of years, we've been working with ARM to try and nail down what the architectural intent for these is and capture that in precise models. Who is we? We is Ben and Thibaut, and other people. So there's a nice paper in ESOP, and then another nice paper in an older ESOP, and a bunch of work in progress, because this nailed down a lot of things, but not quite everything. And then a bunch of work also with OHAD on exceptions, and then also a bunch of mostly complementary work going on inside ARM with JavaScript et al. So none of this is kind of totally nailed down, but it's kind of getting there. Right? It's kind of approaching a decent foundation for verification. So I don't want to talk about this very much, but just to give you some very vague flavor, this is one of Ben's relaxed virtual memory litmus tests that just illustrate some particular, semantic design question that you have to think about. And I'm not going to even read this out, but it's a test. It sets up, some page table initial state, somewhat symbolically, and it has a couple of threads, but now the threads do TLB maintenance, and there are exception handlers to figure things out, and so on. And you can see in the execution, there are a bunch of reads and writes and a bunch of edges, but some of these reads are now translation reads, related to the instructions that did the address translation that created those reads, with a bunch of amusing relations over them. And it's totally fascinating talking to the architects about this, because you're up against what the architecture design is and why it is what it is, right? And lots of that is, of course, totally clear to them because they've been designing this architecture for a long time now. And then every so often you say, hey, should this be allowed or not? We have to decide. You're making a model. You have to decide everything. And they say, good question. And then, these are the other pictures in Ben's thesis. It's like humanly doable, but there's quite a few things you have to pay attention. Okay, so I said these are not definitive. There are interesting open problems. So there are some open questions about what the semantic should be, not so many. There are probably quite a few open questions about the interactions between these different features that we've not seriously considered yet. It would be good to have better testing and test generation. We would like to converge with the ARM internal work. All of that is kind of in progress. And I think already we have a sort of decent foundation for quite a bit of verification work. Right? A lot of the things we've done already are not going to change very much. Okay, so we have something almost to work above. Whew, that's something. Can we potentially reason about any of that? Be nice. I'm sorry, I'm out of order. We have two pieces of the foundation. Are they joined together? Surely that's trivial, you say. We just take this paper, and we take that paper, and we take a big stapler, stick them together, and we're done. Oh, if only. So we have previously glued these things together in software tools, right? So all these different tools by us and by Jad and Luke have glued together some version of some relaxed concurrency model with some version of some instruction semantics model. And over the years, these have become more elaborate and more full. So this Euler axiomatic tool by Alistair Armstrong glues together axiomatic models with the full ARM or RISC-V ISA, so Win. The RMM tool uses the full RISC-V ISA, but for engineering reasons, still only fragments of old ARM. But that's good, but we don't have, and nobody has had, an integrated mathematical definition of that combination, right? We have not yet drawn that little line. So right now, even as we speak, Thibaut is trying to draw that line to make a mathematical definition in what we shall now call ROC to precisely define the set of allowed multi-core executions in a way, hopefully, that will be reasonably reusable over future time and not change too often. I mean, surely we will have to change it a bit, but we're trying quite hard to engineer that to make it robust. And there is a very interestingly shaped line, because you have to understand the information that the ISA semantics has to expose to the virtual memory model in order for it to say what it needs to say without it being insanely complicated. And it has to be nice enough in style to support proof and still be executable enough to run tests. Right? Otherwise, we can't validate it ever, and it will be wrong. Okay, so that then is this foundation. And now we ask, can we reason above it? Let us be humble and set our sights low. Can we reason about the sequential part? Okay, that's not very humble, because it's a 400,000 line definition. But maybe we can chop the problem up a bit. So there are two kinds of problem here, which are really very different, right? So one is, can you reason about specific bits of binary code? or maybe code abstracted on some relocations or some register names or some immediate values, but more or less specific bits of binary code. And can you reason about that just in a sequential, sensible fixed translation setting? Well, I mean, maybe you could do that just sort of straight above the definition in a prover if you were very strong and much cleverer than I am. But all that complexity in the instructions really gets in the way. Right? So Michael Samler and Angus Hammond, I think neither of which are here, came up with this scheme which we call Ilaris a couple of years ago. And there are two ideas here. So the first idea is to notice that even though for instructions like that you have that whole page of sale, if you know that you're working on a specific opcode or on an almost specific opcode, and if you know that you only care about the semantics maybe at EL2 and maybe under some other assumptions of other system registers, and maybe on some assumptions that some addresses are aligned, so you won't generate multiple accesses for a memory access, just one single copy atomic access, then this Euler symbolic evaluation tool by Alistair can take that page of sale and simplify it down with symbolic execution to a nice, easy-peasy little trace. Right? So we get rid of a lot of that static complexity with this symbolic execution. Okay? And then you can take those traces and you can feed them into Iris. Well, really, you can instantiate Iris with the language of those traces and make some proof automation above it and actually reason about machine code. Win. And even machine code that does some systems-y things, but in the sequential world. Right? So Angus proved a fact sort of like this about the first 49 instructions of one of the PKVM exception handlers. Right? So this is a piece of code actually written in assembly that runs when you first take a fault into PKVM from the host. Right? And you can see there's a precondition and a postcondition, and these are both really written down in Iris, but I'm not going to tell you what they are, except to say some of them are a teensy bit subtle, like this one. You know, the next two words of the stack are used by this handler, so we have to own them, and we have to be able to compute their addresses without an overflow in the machine semantics. Right? So there's lots of things like this. You know, they're all little things, but you have to actually have them all nailed down. Open questions. Does this scale to big enough examples? Maybe. Maybe we need to do something different. Could we do it without relying on this external symbolic evaluator? That would be nice. It's not essential for the level of assurance that we think is possible at the end, but it would certainly be nice. Yeah, so, don't know. What about the other half of this sequential problem? Can we reason about arbitrary ARM instructions? Why do we need to do that? We have a hypervisor. Well, we have a hypervisor, but we also have all the host and guest code, which is untrusted. We want to be able to reason about that. But we do not want to reason about that in terms of the full ISA all of the time, because that would be quite annoying. Right? So what we want to do instead is characterize the potential behavior of arbitrary code. And I mean, the hypervisor has to work whatever it does. So this cannot be a very complex property. But for example, you might want to know that in the configuration that PKVM is running, the EL1 and EL0 memory accesses are to end up being to physical addresses which were produced by a legitimate translation. Right? So that's a fact about the whole 430,000 lines of ISA spec, but it's not a very deep fact. And conveniently, Thomas and other Thomas have been proving that kind of fact about this cherry-enabled ARM, Morello, and the same kind of thing you can use for this. So this is mechanized proof in Isabelle, honest to goodness proof of the sale, about the sale-generated Isabelle. Yay to Isabelle and Thomas for being able to handle definitions of this scale. It's not totally trivial. Open questions. It would be nice not essential for us, but it would be nice not to have two different provers in the story. Can you do similar proofs in Rock without it complaining? Rock is not very friends with at least the current sale to Rock export. It just explodes terribly. Totally can't handle it. Maybe we could do differently, maybe with a deeper embedding of the sale into Rock. I don't know. Good question. Okay, so that was reasoning sequentially. Dominic.
So you have these two A1 and two A2. Have you thought about how to connect the two together?
In a hand-wavy way. Some of that, I think I will draw you another cartoon picture later that will speak to that a little bit. I mean, I kind of understand how a proof might go that connects them together. Before we get to that, what about the concurrent part? Okay, so for user RMA, we have models in these different styles. Operational, axiomatic, promising, all good in their different ways. Proved equivalent for some fragments. That's great. But these models, not so much the models, but really the ARM architecture is hopelessly non-compositional. Right? Just everything is totally global. Right? These only define the semantics of whole programs. And for axiomatic models, kind of the others too, they only define the semantics of complete executions. Right? And this is kind of intrinsic to the architecture because ARM allow this load buffering shape. You can have cycles in PO plus RF. Right? You can have perfectly allowed executions like this in which two reads read from the program order future of another thread. So you can have, there is no prefix of this execution, no PO prefix, which is closed under RF. Right? So the prefix, I mean, it's not sort of nonsense, right? It's just intrinsically not very compositional. So that's a bit of a challenge. Worse, when you have mutable address translation and you have self-modifying code, both of which we have here, and this may be a shock to you, there isn't a program. Programs don't exist. Right? There really isn't a program. There's nothing to do compositionality on, okay, a priori. There's just an initial machine state. Okay, that sucks. Well, no, it doesn't suck. It's great. It's a lovely opportunity with interesting problems. Okay, can we pretend this doesn't exist? Regrettably, no, because PKVM is quite concurrent with itself and its guests. Right now, within itself, it's kind of simply locked in some ways, but that is getting worse even as we speak. Well, at least on Monday it will be, when the people in the Google office make it more relaxed. Right? But it is manipulating the address translation it uses for its own execution. It's dynamically loading some initial code. It manages these address translations of the host and the guests, but those are doing translations while it's managing the page tables and so on. And it has to do enough TLB management to ensure that some key ARM architecture requirements are never broken. Right? So we have to be able to reason about this stuff, but nonetheless, most of the reasoning about the C code of the hypervisor, you want to be under the isolated, sequential, sensible fixed translation assumptions. Right? So how can we establish that that's a sound abstraction, and for the bits of concurrency that are not like that, how do we reason about those? Those are good problems. Well, let's look at it first. So this virtual memory semantics of ARM, as Ben has explained to us, is insanely complicated. Well, not insanely, it's quite complicated. But the way PKVM uses it is kind of special. So for example, it's good, well-behaved code. It is not going to violate this ARM break before make discipline. Right? So we think we can, and Jean-Pierre Faribault and Ben have been working away to build what we call a simplified model. We do need a better name for that. A simplified model which is kind of like a data race-free SC model. Right? We can build into this model that the hypervisor is not allowed to violate break before make, for example, and just not give semantics in that case, and thereby make that a proof obligation on the higher level verification. And hypothetically, we can prove that sound above the architecture, and then that gives us a basis for reasoning sequentially about the bulk of the C code. Open problem? Well, actually do it. What about the remaining tricky cases? Well, we kind of think it would be nice to have a program logic above that simplified model. The model doesn't exist yet, so obviously we don't know how this will work. But conveniently, Zongyuan, who is here, and Angus, who is still asleep, have figured out how to do a program logic above the ARM user axiomatic model, which for quite a few years we have thought was just impossible. So, yay. And it's even done in a way which is kind of generic in what the axiomatic model actually is. So we have some hope that this will be generalizable to other axiomatic models, or in particular to some presentation of this simplified model that we were talking about. There are lots of open problems. So this already still doesn't cover the nice reasoning about coherence. It's really a logic for reasoning about the OB order, the happens before order of ARM. And it does use some version of the honest interface to the ISA, but it isn't actually plugged together with the full ISA yet. And then we need to generalize it to the system stuff. So those are all big questions, but identifiable, articulatable questions. Okay, now we return back to Dominique's question. How do we envisage some of these pieces might be fitted together, into a proof? I emphasize envisage. Okay, this is entirely vaporware. But okay, first we have to imagine what the spec will look like. What is the top level spec of a hypervisor? Right. Well, this hypervisor provides an abstraction to the arbitrary host and guests, which is more or less the same as the ARM abstraction. Right? All the instructions, all the normal ARM concurrency, stage 1 address translation, all the stuff that EL1, all the system stuff that EL1 can do, all of that is just directly provided by the hypervisor to their clients. Right? So it provides an abstraction just like the ARM spec, which is, the ISA glued onto the concurrency model via this nice interface, except that these stage 2 translation functions that I showed you the types of, and the semantics for EL exception and return to and from EL2 have to be ripped out. That's kind of easy because there are nice function interfaces within that spec to do the ripping along. And some other now irrelevant EL2 state has to be ripped out of the model. And the concurrency model has to be extended with sort of new API events for those things and new magical semantics for how the hypercalls behave. And that magical semantics is essentially the more or less hardware thread local spec of each of the PKVM exception handler pieces. And then there's some other complications which I shall skip over. But so that's sort of the spec, and then one can think about the correctness statement that one would aim for. There are, I'm sorry, quite a lot of words on this slide, but just sort of quickly, what you would like to prove is that for any supported hardware configuration, that's already a fairly big quantifier, for any legal choice of the initial runtime, where it's positioned in memory and things like that, that's not too big a deal, although there is an engineering challenge. For any contents of the PKVM initial state that satisfy a great big fat invariant, that we plan to test, not prove, for any arbitrary content of the non-PKVM initial state, any complete execution of the underlying machine semantics together with these two gives you a sort of similar execution of this right-hand semantics, except we'd like the EL2 parts replaced. It's sort of the concrete theorem that you think you should be able to prove. Yeah? Or in pictures, any execution of this thing should be, with some erasure and slight other surgery, be an execution of the nice top-level spec. And this uses, so we aim in the course of that to use this simplified model. So what's the soundness of the simplified model? So the simplified model sort of just fits in the same place. Right? It has the same concurrency interface, and under the assumption that the ISA satisfies the whole ISA properties proved in Isabel by Thomas about translation, then any execution about this should be an execution about that. And this is a very lovely picture in a way that may not be totally obvious, because all of this yellow stuff doesn't involve anything about the instruction semantics, which is large and unwieldy, except those properties. Does that slightly answer your question? And then the proof of the proof of this will involve some sort of DRF-like reasoning. Dominique looks skeptical. Perfectly properly. There are a lot of moving parts. I mean, it took us a while to even get to this level of clarity. Yeah. Okay, so this part is definitely vaporware, but it's like not totally implausible. Yeah, that is an open problem. Okay, so now I'm going to have to abbreviate quite a bit what's on the slides. But I've been talking about ARM, but you mostly don't want to reason about ARM. Most of the code is in C. You want to reason about the C in its terms. Otherwise, maintainability and proof effort, obviously a non-starter. For C, very conveniently, we just happen to have in our back pockets a semantics of C, which Kevin Marian has been working on these many years, and it's quite well validated. It's good. We've got memory object models that we can believe in. It's good. Thanks also to Rodolphe and Michael in MPI at the time for some of that. Can we reason above that? Lots of people have done some reasoning about C, many of them in this room. And there are lots and lots of cool ways to do it, all of which have done impressive examples. But I think it is, probably none of those people would disagree, we have still not reached the happy state where this is nice and easy and maintainable and doable even for low-level Linux kernel idioms, not compcert C, and integratable with all of this concurrency stuff. So there is a whole big story about this, developing separation logic refinement type systems to try to do slightly less annoying reasoning about C. And we've had two experiments which are ongoing, CN and refined C. CN by Christopher Poulter and Dhruv Makwana and Thomas Sewell and Kevin Marian and Neil Krishnaswamy, who is here, and refined C by our friends in MPI, Michael Samler and Rodolphe Lepigre and others. So these are both good. If I just show you very quickly some CN stuff, you annotate code with separation logic assertions, essentially, but in some quite limited fragment to try to make the proof automation reasonably predictable. That's the top-level punchline. And it kind of works, even for some of this low-level code. This is one of the functions from a PKVM buddy allocator, which does exclusive OR on pointer bits and lots of integer pointer casts and what have you. And it's kind of a readable spec, and with some predicates and things that you can understand, and it kind of works. It doesn't work great, and there is a very open problem. Now, is this going to scale to all of PKVMC, or do we need something substantially different? And then there are lots of other more specific open questions, which I will gloss over. You will notice this is hanging in midair compared to this. You will have noticed that. We imagine, and Thibaut and I and a master student from Munich, Mate Polet, have done some experiments on translation validation to relate these two. And this is interestingly different from the normal translation validation problem, because here, in principle, you have a whole CN verification of the above in a nice separation logic, which we can exploit. And we have like all the debug information for the binary produced by classic Clang, which we can exploit. Right? So maybe we can do that, but we haven't done it. That's a big question. Okay, up to now, yeah, soon. I guess we started a bit late. Did we start late?
Yeah, 5 minutes late.
Okay, maybe I'll not be totally out of time. That would be unusual. Yeah, this is like a classic verification story. Okay, we should never do the classic verification story. It's no good. Right? I mean, it's good for writing papers in POPL. It's really good for that. But you have like this terrible cost-benefit function, right? And this room gives me like the ideal setup in which to explain it, because you have this line, so vertical axis reward, horizontal axis effort, right? And it goes along this line, further along this line. Each of these is like, you know, a very sad PhD student. And then it goes along this line, and then, yeah, those things are very sad postdocs, and it goes along this line. This thing is a very sad funding body, and that thing over there, a very sad industry collaborator, and then it goes along here, and then it goes along here, and then it goes along, and then it goes over here somewhere, and then if you're sufficiently fortunate and skilled and everything, there's like a step function to, yay, we've got a proof! It's terrible. It's just totally terrible. And in all of this time, what you could say to your, you know, conventional engineering development collaborators is, yeah, well, just be patient. Just hang in there. We're working on it. We are working on it. See these papers that you don't want to read? We're working on it. It's terrible. We should never do that. We should never do only that. Right? So what do we have to do to engage with a development team? We have to understand how they develop things. How do they develop things? They do test and debug development. And they're very clever, so they can make that work. They are really clever, and they can make that work really quite well, but that's what they do. So we have a scheme here to, instead of just do all of this proof, actually make these specs very straightforwardly testable. The scheme is not entirely in place yet. Rini Banerjee, who is not here this morning, is beavering away working on that. It turns out that the restricted expressiveness that makes CN good for proof, thanks Neil, also makes it rather testable. Right? You don't have to go away and say, oh, I will just search for an existential split of the heap now, right? Which is a rather tiresome thing to do. So we would like to provide them, and we think we can quite soon provide them, with an infrastructure in which these rather rich specs can nonetheless be tested at runtime in conventional execution. Indeed, in conventional execution, integrated online with the hypervisor code at EL2, a bit slowly, but nonetheless, or potentially running offline, which actually the devs seem to prefer the idea of. And then, that together with a hopefully readable specification language, which is suitably but not offensively noisily integrated with the C is at least a plausible way that we can get a slightly better graph that, maybe goes up a bit, going from over there to over there. There's some open questions. Make it really work. Actually build infrastructure for driving the thing. We've got some of that. Script good tests. Generate good tests. A whole lot of interesting questions there, some of which we're discussing with our UPenn friends. Lots of things one can do. Okay, so far, I haven't actually talked about any verification of the actual code to speak of. Obviously, there's going to be a fair bit of that. Nor have I talked about how one nails down what this top-level spec actually looks like in any detail. So we could spend the next however long, polishing up all of these tools and then do that. Or we could try it now. But we haven't got any tools that work. How can we write a spec with no tools? Oh, we could just write something on paper in a theorem prover. Oh, but then we can't test it and nobody except us can read it. So instead, we do a mad thing, which I'm very proud of, which is to understand that your favoritist programming language. What's your favorite programming language? You're all wrong. Hmm? You win. I'm not sure what you win. A lifetime of pain, probably. But C, even if it's not all of your favorite language, it is the dev team's favorite language, or possibly least favorite language, but it's the one they use. C is a great specification language. C is just the bits as a specification language. It needs zero investment in weird, wonky tooling, or zero investment in educating people how to read specs. And you can just run it. It's great. So we prototype the top-level specification, PKVM, in executable C code that runs at EL2 and everything with, all the integrated with the concurrency model of the hypervisor. Ben and Thibaut and David Caliper-Mershignac and I and Kavan Mumerian have been working on that recently. And we now have a top-level specification of the whole thing that is, well, A, is very instructive for us. That's a first benefit. But B, does actually run. We haven't tested it very much yet. If this conference had been a month later, maybe we would have. And you can't prove anything about it. But these are specs which you can discuss with the dev team very straightforwardly. And the scheme we have in mind is to translate these, hopefully rather straightforwardly, into the CN spec language, which may need to be jazzed up in some minor ways, and it will need a somewhat fancier separation logic at the end of the day. But a lot of this should just translate rather directly. Right? So, some kind of assertion checking on steroids, right? So we really compute in C reasonably efficient C representations of the abstract state that you might have written down as a bunch of rock data types if you were that way inclined, right? So we walk over the honest to goodness page tables at the appropriate points in the code when the appropriate locks are taken and compute their interpretation as finite maps and such like, and manipulate those in the spec. So you get quite nice specs in which the spec of a hypercall says, well, you take this thing away from that page, that address translation finite mapping, and you add it to that one when you donate a page from here to there. Looks good. Okay, high time I stopped. Can we reason about the security of concurrent systems code? Definitely not. But kind of maybe one day soon. Right? I wouldn't wish to make too strong a statement, but I mean, we are very seriously aiming at that, and I think it is feasible. The sort of slightly wider point that I want to make is that there are a whole lot of interesting problems, like really interesting problems, and ones that people actually care about out there in the world, not just in the POPL community, and that one wouldn't even start to see some of these problems until you at least try in your imagination to try to stitch these things together at scale, and to, at least aim at all of the sort of for real version characteristics which I mentioned here at the beginning. This is, of course, only one scheme, and Gregory and his fellows will tell you about some quite closely related but different schemes in some other talks, and other people have done other verifications of hypervisors. But I think it's very instructive to try and, draw this, make this, this is a cartoon picture, right? But to try to make this cartoon picture a real picture is quite educational and fun, and potentially even useful, who knows. With that, thank you for your attention.
Well, we have time for questions.
Hey, Peter, fantastic talk, as usual. Two questions. One is this green part relating C to ARM. What kind of verified compiler can you use? Is Adapt Concept has all the features that you need for that? And the second question is about what about other hardware manufacturer? Like how much of this work effort can be adapted for Intel or NVIDIA, whatever?
So for the first question,
Can you repeat the first question?
So the first question is, for this translation validation part, what kind of verified compiler could you possibly use? And the answer is no kind of verified compiler, because Android is built with Clang. It will keep on being built with Clang. This is kind of immutable. So we really do imagine doing translation validation, not compiler correctness proof. As I said, we have not remotely done this. We've sort of dabbled with it a bit, and Corridor has some pictures with the control flow graph of a predecessor of PKVM at 00 and 01 and 02, and we kind of scratch our heads and think about that. I think it's sort of general translation validation of Clang is still a very open problem, although I think even that people could do a lot more than they have done if you do it by phase, by optimization pass very carefully. For this, it does sort of seem within the realms of plausibility that we can do it. Maybe with some optimization turned off, but if you do that, then at least you limit any errors in PKVM to the there are optimization bugs problem. We kind of have to do this because I didn't say this. This is the only semantics at the end of the day that we can get real confidence in, especially for the system stuff, right? We don't see ourselves, this is pretty well validated, but you can't directly extend that to all the system stuff. Okay. The second question I now forget. Oh, yes. How much of this would apply to other architectures? So I think a lot of the tooling would apply. There is now a chunk of x86 SAIL model that covers some system stuff which the ACL2 people developed, which we've imported into SAIL, for example. The concurrency model is quite different. No one has looked at the relaxed virtual memory of Intel. I have no idea what that's like. This stuff would be kind of similar. For RISC-V, it would probably be pretty similar. A lot of this is common.
I think we have time for a couple more questions. Well, yeah, we can go over time. No worries. I think it was first.
Yeah, thanks. Thanks for the interesting talk. And you've presented a bunch of very difficult challenges or problems. And one of the ones you mentioned at the beginning, I was still curious that you didn't resolve how you would maintain all of this, right? Like you have one version of the microarchitecture that you have now. What happens when a new one comes in? What happens when they continue to develop the hypervisor? How can we hope to maintain this without a lot of pain, like you said?
So excellent question. How can we hope to maintain any of this without going mad? So one part of this is to, broadly, one would hope to make the things which are liable to change as predictably automated as possible. And the other thing is to make the verification of the C code, like, so this is CN annotated PKVM code. So the developer, or really the verifier, has to write this. But I think we can plausibly hope that the developer can read most of this and talk about it. And then, there would be a burden in updating this when the code changes, no question. But hopefully a rather smaller burden than if you had a whole enormous, very low-level proof. So you would aim, in another instance, to make the simplified model of abstracting from some of the virtual memory properties to let you ignore fine details in the virtual memory semantics. And it does to some extent. But I'm not claiming that the magic bullet has been provided.
So just a question also on composition between what you do at the C level, and I guess some things have to be done at the assembly level. Like, how do you see that going?
Okay, so the relationship between C and assembly is really interesting. So the first thing to say about it is that except for that exception handler, let me just get the cartoon back again, except for that exception handler that I spoke of, all the assembly in the code is very special. Right? It's just inline assembly to do a TLB maintenance or a barrier instruction. Right? So we do not want even a generic composition of arbitrary C and arbitrary assembly that mutates C data structures. Fortunately, not necessary for this scenario, although that's also a good thing to do, but there isn't the kind of code that the devs write for this. More generally, okay, so we might have we do have some separation logic, essentially assertions annotating the C code up here. And the idea which Mette Polak pushed a bit in his master's dissertation as an experiment is to take those assertions which are about the C abstract machine state and reinterpret them about the ARM state using the debug information to tell you what they mean. Right? That seems to me a rather straightforward thing that people should have done 10 years ago. And it's super powerful because you get to know sort of automatically the concrete thing that has to be sort of automatically verified down here if you want to do the translation validation. And down here, I mean, ultimately this separation logic will have to know some things about the simplified model for the TLBIs and so on. So that will appear in our reasoning about this. Well, actually about our reasoning not above this, but above this together with the simplified model that I spoke of. Joe.
Yeah. Do you have a sense of how many security vulnerabilities rely on some of these very low-level details? Like, let's say I was very naive and I wanted to do my verification assuming SC. Are there attacks that we know of that I would miss in doing my verification?
So my feeling is there are not very many known relaxed memory dependent attacks because there are lower hanging fruits for attackers to go for. I mean, if we were aiming for sort of a security bug finding project, we would be doing different things. Right? We really are aiming for high assurance at the end of the day. Are there any bugs at all? So we have not done enough verification to even have, in principle, a possibility of finding bugs, but we have done quite a bunch of reading of the code, especially in writing these top-level specs. And Ben and Kevin and Thibaut and David came up with a list of like 7 questions that we sent to the devs quite recently, of which about half of them or something, maybe a bit more than half, they said, yes, that's a bug. And one of them was, oops, in resolving some Git conflict, they had managed to omit the TLB maintenance during initialization. I mean, that's probably exploitable, although there might be easier exploits.
Since there's no further question, thanks again for the wonderful talk, Peter.
Thank you.
I wanted to ask if speculative execution changes any of this picture, but that might take too long. So
A lot of this relaxed memory semantics arises from speculative execution. Right? I mean, there's another thing about speculation barriers that we're not in a position to reason about.
right.
There should be a. Oh, do you want this? Do you want this?
Yes, please. Thank you.
All right. The last talk of the first session is given by Elias Storm. No, it's Dominique De Vries, who is talking to us about secure calling convention for cherry capability machines in practice.
Hi. Yes, so hi everyone. My name is not Elias Storma, so I'm Dominique De Vries. Yes, apologies. Elias is supposedly at a wedding somewhere and was unable to give the talk, so I am filling in. I should start by a disclaimer. So when we decided to submit here, we were not yet aware of that there was a different interesting workshop very related to these things. So at some point we decided to just submit to both places. If you are one of the unfortunate people who have attended both, then I apologize, but I hope there's not too many of you. So what I will talk about is a much narrower problem than what Peter has been talking about, but I hope still interesting.
Possibly soluble.
Possibly, yes. Let's take a look. It's definitely not a solved problem. It's a work in progress, as you will hear. So first, this is about cherry capability machines, which I hope some of you are aware of. They're, to give you an idea of, for those of you who don't know what that means this is a class of instruction sets that offer a very nice, if you ask me, a very nice type of security primitives, very different than hypervisor machinery and page tables and so on. What you get instead, or sometimes in addition, like on Cherry, is a notion of capabilities. So what is a capability? You can think of it as a fat pointer. So a pointer that doesn't just point somewhere in memory. It still points somewhere in memory. There's this cursor position. But additionally, it has some bounds information. So there's every capability comes with a lower bound and an upper bound, and that tells you which part of memory you can use this capability for addressing. So if you try to use the capability to read or write somewhere else in memory, the processor will tell you that's not allowed. Capabilities also have some permissions that tell you whether you're allowed to read or write or execute. There are some other permissions that are not less relevant for this talk. So benefits. You get some very sort of fine-grained way to enforce memory safety. And the hardware sort of does it all in the background. And while your code is executing, the hardware is continuously checking all sorts of memory bounds on your memory accesses. And hardware people are able to do this very nicely in parallel with the actual execution of your code. So you pay relatively little for all of this hardware enforcement of memory bounds. You can actually use this essentially for two things. You can use it to enforce spatial memory safety. If you have an array and you try and read from it, that transparently the hardware will check that you're reading inside the bounds of the arrays, not outside. And that gives you a way of sort of a kind of sanitizer on steroids that runs sort of during the actual execution of your code. A second and maybe a more important usage of capability machine primitives is for doing software compartmentalization. So if you have a software system, you can sort of chop it up into pieces, give access to some parts of memory to component A, give some other component access to other memory, etc., and then have some sort of a context switching, but a very cheap form of context switching when the components invoke each other. An important question is how fine can we make this compartmentalization? What are the components? If you have a browser, maybe every tab is a component. The Cherry people have demonstrated nicely that this is possible. But what if we want to go further? What if we want to make if we have an object-oriented application, maybe we want to make every individual object a compartment. Or if we're writing in a functional language, maybe every closure should be a separate compartment. And that means there's a very big amount of compartments, and you need to make compartments cost very little, right, to make this feasible. On Cherry BSD, that's currently not the case. So particularly every compartment on Cherry BSD has its own stack, and the stack needs to be a certain size to make things work. So that means you cannot make compartments too small because you're going to have to reserve a lot of stacks, and that's going to cost way too much memory. The compartments communicate through a trusted intermediary that is going to switch stacks when you switch from one compartment to another. What we're interested here in this work is, can we get rid of these separate stacks? Can we give all compartments, can we make all these compartments share the same stack in a secure way, so that one compartment isn't able to access the stack frames of another? And that would allow, we hope, a more granular compartmentalization, faster communication between compartments. So there's two things you need for this. So first, and I will talk about both, you need a return encapsulation. When you create a return pointer, you need to somehow encapsulate that so that the callee isn't able to use it in a way that he or she shouldn't be able to. And second, you need to do stack revocation. So when you give a stack pointer or a return pointer to some callee, the callee returns, and then you invoke another callee a second time. That old stack pointer and that old return pointer should no longer be usable, right? And if you don't do that, then you're going to get into problems. So let me focus a bit more. So return encapsulation. Imagine we have a stack growing downward. We have a caller stack frame over there. So when you do a call, you're essentially you're giving some authority to the callee. Essentially, in this case, that means you're giving the callee access to whatever remains of the stack after you sort of reserve your own part. When the callee returns to you, you want somehow to get back your original authority, including your own stack frame. But you don't want the callee to have access to that. You need to create a return pointer that somehow reestablishes your authority for your code without the callee having the ability to do that. A second problem is stack revocation. So when your callee has returned to you, you want to be sure So you want to be sure that old return pointers, old stack pointers are no longer available. And this is particularly hard because the callee has the ability to store capabilities all the way down in this stack, right? There's relatively easy ways to prevent the callee from storing capabilities elsewhere in the stack, elsewhere in memory, I apologize. However, in this, it's very hard to prevent them from storing something in the stack because they're going to get access to that part of the stack again when you invoke them the second time. Okay. So this is a bit technical. I hope the explanation is more or less clear. one way to do this is by clearing a lot of stack memory, which actually happens in some systems, like Chariot, yeah, I'm not going to go into too much details on that now. What this talk is about is there's a number of theoretical proposals from some of which I was involved with myself, not all of them, particularly building on linear capabilities, local capabilities, uninitialized capabilities, directed capabilities, all different kinds of proposed variants of capabilities, particularly to make it cheap to do this revocation, to somehow prevent a callee from accessing what was in the memory in a previous invocation of the callee. Okay. So these proposals are all very formally sound, but very far away, but still a bit far away from reality. They often use, they typically use a sort of theoretical capability machine that has abstracted away from some of the realities of real capability machines like Morago, like Cherry, RISC-V, etc. And that's the topic of this talk. So can we make these sort of theoretical proposals more realistic? And particularly, we do three things to try and get closer to that. We have worked, on the one hand, there's an issue between applying these proposals in the presence of something called capability compression. I will talk more about that. There's an issue, of course, you need to implement them. And particularly, I will talk about an implementation in LLVM that we have made of this. And then finally, we are doing some benchmarking to see how costly these proposals actually are in practice. So capability compression, what do I mean by that? So this is a feature of Cherry. So if you do capabilities naively, then on a 64-bit machine, your capabilities will be 256 bits because you have to keep track of 3 addresses, lower bound, upper bound, and an intermediate address, and then some more permission stuff, which is too large, too costly, has a lot of impacts on the performance of caches and so on, and apparently for hardware systems people, this is just too much. For that purpose, Cherry uses something called capability compression, which essentially is a sort of lossy compression of capabilities that saves memory, but at the same time makes capabilities less precise, and this breaks particularly the secure calling conventions that I mentioned. Second, implementation in a mature C++ compiler, and finally the benchmarking. Let me go into a bit more detail. Capability compression. So there's a very clever compression scheme used in Cherry machines. There's, as far as I understand, several variants of this, but they all sort of have the same principles. They represent capabilities in a sort of floating point encoding, where the 3 addresses share some sort of common parts, like the exponent is shared, this exponent here is shared between the lower bound and the upper bound, etc. You can save a lot of bits that way, but it has certain consequences, particularly, essentially, the bigger your capability, the coarser the bounds need to be aligned. Okay. Why is that an issue? Because these theoretical calling conventions, they ignore capability compression. And that conflicts with an important operation that happens all the time in those conventions, namely stack splitting. What does that mean? We have a stack pointer pointing from there to there. We want to invoke a callee, and that means we need to split up our stack pointer precisely at the boundary between these two stack frames. However, the stack, as you can imagine, it should be quite big. If you want to split precisely at this point, it's not going to be very well aligned, and that means that is essentially a sort of fundamental conflict between the two approaches. if you do some calculations, then if we want, since we can only assume that the split between the stack frames is going to be 16 byte aligned, that means the maximum stack size we can support is 16 kibibytes, which is way too small. If you look at Linux, for example, default stack size is 10 mebibytes, so a lot bigger. So we are proposing a solution here, which is to split up the stack into two parts, something we call an active stack, something we call a reserve stack, where the reserve stack is much better aligned, but the active stack is sort of the stack that you're using in one stack frame. There are some issues to make this work, but you can read a bit more about that in the paper. Particularly, at certain points, we need to replenish the active stack, which means turn this sort of active stack that is smaller than a certain limit into a larger version by taking some authority from the reserve stack, putting it in the active stack, and continuing. Okay. Some considerations that we haven't solved yet, or where we have some ideas, but which we still need to sort of validate and test and so on. Where should this reserve stack capability be stored? Current ideas just at the bottom of the active stack. Can components share this replenishment algorithm? Do we need to duplicate it in all components? We think so, but practical consequences need to be investigated. Compatibility with stack objects, there's a certain issue we need to take care of, that we don't accidentally replenish stack objects rather than, but we only do that for the stack pointer. There's a certain case where this can happen. And then finally, where and when do we need to check whether replenishment is necessary? Our current idea is to do this by the caller on every call. So all of these things need to be validated, but we think we can make this work. Second contribution in this work is an implementation in LLVM. So why do we want to do this? We want to investigate in practice these theoretical calling conventions. Can we make this a reality? Can we benchmark them to actually see how costly these things actually are? And also compare. Maybe if we, particularly, we don't just want to implement these different calling conventions, we also want to have sort of partial implementations that implement parts of the measures of certain calling conventions so that we can sort of quantify the individual cost of each of the sort of partial measures, so that we can maybe see where some improvements are still needed. Why LLVM? LLVM is quite standard for Cherry, and LLVM is quite mature, so we can benchmark on sort of hopefully on real C and C++ code. There's two orthogonal components, this return encapsulation and stack revocation, and that actually means we can investigate several options for both of these components. For the return encapsulation, we can essentially work with something called sentry capabilities, or with indirect sentry, where we think indirect sentry has certain advantages, but I won't go into detail here. So there's some detail here. Essentially, sentry capabilities require that for every encapsulated return pointer, the code needs to be stored close to the data that the return pointer carries, which is annoying. Essentially, it means you need to store some trampoline code on the stack, which systems people don't like, et cetera, et cetera. So indirect sentry capabilities should allow us to do better. Stack revocation, there as well, there's many options. We can work with local capabilities and stack clearing. We can work with alternative proposals, for example, uninitialized capabilities, which we have proposed in collaboration with some people in Aarhus. And there's other proposals that we might want to look into. An uninitialized capability essentially allows you to represent ownership of a certain region where you have read and write access to some parts, but only write part to some other part. And when you initialize this, you can sort of shift the bounds downwards. So this is something that we have proposed, which works well in theory, which we want to investigate whether it can work in practice. So that means we have a sort of design space that we want to explore. We want to focus on these things particularly as stack revocation, no stack revocation, working with uninitialized capabilities or with local capabilities and stack clearing, return encapsulation. We want to explore these trampoline and indirect sentries. Some of these are implemented, as you can see with the full circles, the filled circles, and some of these are on the agenda. For benchmarking, we want to, this is sort of work in progress. This is the part that is most work in progress. We want to benchmark a bunch of these variants, including these ones, but also sort of partially implemented versions of these ones to sort of quantify the individual, the cost of individual measures within these calling conventions. And for all of these calling conventions, we want to look at different metrics, not just execution speed, but also stack usage, how much stack are we wasting, for example, with this trampoline code, binary size, how much code do we need to generate to do, for example, this stack replenishing, etc. Compatibility, that's the hardest to measure, but how compatible are these calling conventions with sort of standard C idioms or widely used C idioms? How do we measure that? Currently, we're working with a sort of random testing framework, which focuses particularly on like functions with different signatures and with variadic arguments and so on. There's other things we would like to measure which are not covered by this testing suite, so we're still looking for all other testing suites to also work with. We also want to get to sort of a real C code, but we're not there yet. Which hardware can we use? For many of these things, there's no hardware available. We can work with the SEO emulator, but it's not psycho-accurate. So we're looking at, for example, modifying a simple RTL implementation or working with a psycho-accurate simulator. Which software do we want to measure? Currently, micro benchmarks. We would like to get to macro benchmarks, but we don't know yet what is possible there. And that's it. So conclusion. We want to make these sort of theoretical calling conventions a bit more practical, or at least investigate how feasible that is, how advantageous that is, etc. And we are contributing towards that goal with these 3 different contributions.
Thank you, Domi. All right. Are there questions from the audience, or are there people that attended the talk from the other workshop and remember those questions and want to ask them again? We are slightly over time, so we don't have much time for many questions, but yes.
It's a very small question, and the answer might well be no. I wonder whether for this last benchmarking point, whether you could do as well or better with less effort to, instead of making a Gem 5 version, which is a whole lot of work, capture detailed instruction traces and have a plausible cost model based on roughly Morello timing but different.
Yes, so exactly. So we talked about this with Robert Watson at some point, I think on Wednesday or on Tuesday, and he also suggested something along these lines, to just have the SEO emulator, for example, just generate memory traces and then indeed infer sort of timings from some cost model. Even a very simple one could give you a sort of rough idea of the performance you could expect in reality.
Or actually running on Morello, but with capabilities somehow managed around, so it wasn't in the way.
I am. Okay, another potentially good idea, yes. Apparently you can also use the Gem 5 cache simulator or the Gem 5 memory model without using the full simulator, so that's another option. So this is what we're investigating for the moment still.
Well, thanks again, Domi. Before you applaud, a couple of things. There's still a short talk session at the end of the 3rd session today, which is free. So please feel free to come up and present some short talks. I'm looking at you. I'm looking at you, Marco Vassen. I'm looking at you, Katalin. So, no, you're all welcome to come and present short talks. And remember, if you're the speakers from the next sessions, to come up and test your equipment. As you've seen, there's delays to be expected. Thanks again, Domi. And there's a break now.
Welcome back. It's 11, so I think maybe a few more people are coming in, but we're about ready to start. Okay, so welcome back to the to this session. We have 4 talks on defenses against side channel attacks, and the first talk today is from Yao Wang, who will talk about mitigations for serverless applications. Go for it.
Hi. Thank you for the introduction. Today I'm going to talk about our ongoing work with my supervisor Asta at the Systopia lab at the University of British Columbia. This work is about mitigating microarchitectural side channel for serverless applications. And I will tell you about what's the problem here, what's our insight, and what's our current solution. This is work in progress, so I'm happy to take any feedbacks and have further discussion. So let's start with the serverless architecture. Today, serverless platforms run serverless functions from different tenants on a shared server to achieve multi-tenancy. Even though serverless functions are from different tenants run in logically isolated compartments, for example, the virtual machine or Docker containers, they end up with sharing the hardware resources, including CPU, cache, RAM, etc. And the resources sharing in serverless leads to microarchitectural side channel. When one of the tenants become an adversary, the adversary can monitor the shared resources usage. And if the resources usage of the victim function is correlated with secrets, the adversary can infer the secrets of the victim according to its observation of the resources usage. But how does this observation like secrets? Let's assume that we have a serverless function whose source code is public, but all the user's input are secret. It takes my user secret, check my passport, and look up my salary with my social insurance number. However, I don't want to let anyone know my passport, nor my social insurance number. But meanwhile, we assume that the adversary have 2 types of observations. First, the program's execution time, and second, the cache access pattern, such that the adversary can carry out the corresponding timing side channel and cache side channel. First, by observing execution time, the adversary can infer if the branch is taken when it notices that the program takes a longer execution path as it has a longer execution time. Or the branch is not taken when the program has a shorter execution time, so that leaks the value of the condition. With cache side channels, the adversary can infer the value of the key in the array or map accesses. For example, using prime and probe attack, the adversary can first prime the cache with its own data and let the victim execute. After victim's execution, he will evict some data from the cache. Then the adversary can access its own data again to get a cache hits and misses pattern. Different keys and leads to different access hits and misses pattern, and it tells the adversary what key the victim is using. So in this case, that's my social insurance number. Well, in fact, more user secret can be leaked. Examples include personal identifiable information, login credentials, online purchase information. And to show the feasibility of such attacks in serverless environment, we are currently actively working on constructing the last level cache side channel attack on the V8 engine. Prior work proposed constant time to address this problem. Since the attack arises from the resources usage variability, previous researchers pointed out 3 source of variabilities. First, branches and indirect calls on secret value. Second, memory accesses with secret indexes. Third, variable time instructions with secret operands. At a high level, constant time execution requires eliminating all these variabilities in your program so that the execution of the program is regardless of the secret. There are 2 general approaches to achieve constant time execution. The first approach is to ask the developers to write constant time code and using verification tool to check if the handwritten constant time code is really constant time or not. The verification has various implementation. You can use empirical fast testing type system or symbolic execution. However, writing constant code is not easy, and also the compiler might not respect the source code level constant time property and violate it during optimization passes. The second approach is to use to generate constant time code automatically. This requires two phases to achieve end-to-end constant time execution. We first need to use transformation tools to convert non-constant time code to constant time code. Then we have to use preservation tool to compile the constant time code into constant time machine code. So far, most tools focus on cryptography libraries written in domain-specific languages or static type languages. But what about serverless applications? Well, due to the limitations addressed above, prior work is not applicable to serverless domain because, first, writing constant time code is difficult, even for cryptography library developers, and it will be extremely hard for serverless developers without security expertise. Second, DSL is not an appealing choice for them because serverless developers tend to use feature-rich languages like JavaScript and Python. Thus, these serverless languages have language runtime that may violate constant time property when interpreting the language bytecode or doing compilation and optimizations. So here we present our solution, Scooty. Scooty provides automatic microarchitectural side channel mitigations for serverless applications. We currently focus on applications written in JavaScript, which is the most popular language in serverless environments. At a high level, Scooty modifies the JavaScript V8 engine to automatically transform non-constant time JavaScript code into constant time JavaScript code and ensure its constant time execution at runtime. So this is the overview of our modified V8 workflow. After using the vanilla V8 component to parse the source code, the CT transformer will transform the regular bytecode into constant time CT bytecode. And the CT interpreter interprets CT bytecode while preserving CT property. The CT bytecode will also be translated to CT CF node, which is another intermediate representation in V8. And CT compiler will take it and generate constant time machine code. In general, we add CT transformer, modify the original interpreter to CT interpreter, original compiler to CT compiler to generate constant code and preserve constant property during execution. In addition, we modify the V8 runtime to obfuscate the secret dependent memory access. And now I will quickly go through the technical challenges involving in implementing Scooty. This includes, first, language runtime can leak secrets, so we need mitigation there. And unlike transforming integers in cryptography libraries, our transformation must be able to handle arbitrary data types. And third, hiding access pattern in complex data types becomes inefficient. And thus, our transformation is now at runtime, so we also want to minimize its runtime overhead. In this presentation, I will only focus on the first three challenges. So first, language runtime leak secrets. This is not a problem for prior work because they do transformation at LLVM-IR level, and they assume that the compiler is trusted to get constant time machine code, and then the CPU can execute the machine code instruction in a constant time manner. Unfortunately, language runtime doesn't interpret bytecode instruction in a constant time manner. During bytecode interpretation and G-compilation, there are fast execution passes that use the value of the operand to improve the performance, but it doesn't ensure the CT constant time execution. So we also need to transform those bytecode handler to ensure the runtime constant time execution. We combine these three components to resolve this problem. We add CT transformer to transform the non-constant time V8 bytecode to CT bytecode. We have CT interpreter, which use transformed bytecode instruction handler to achieve constant time execution of the CT bytecode. We have CT compiler to compile the CT CF nodes and generate constant time machine code. The CT-CF nodes is directly translated from CT bytecode without changing the semantics, so it can preserve the CT property of CT bytecode. And since the bytecode we assume is public, transformation itself is also constant time. So our modification will be sound and complete because we achieve algorithmic constant time transformation at bytecode level and constant time preservation at machine code level. So by composing all these components, we eliminate all the execution variabilities of secret in V8. So far I mentioned transformation so many times, but what does constant time transformation really mean? The CT transformation requires two operations. First is control flow linearization. Another one is data flow linearization. The most important building block for control flow linearization is using bitwise N and bitwise O to select two values, X or E in this example, depending on a secret, without using branches, so that we can use this building block to merge two arbitrary execution paths into one. I have to skip how this bitwise trick works due to time limitation, but this is basically how C-movie instructions works at a source code level. Well, for data flow linearization, we can convert a single array access to accessing the entire array, then keeping the desired result, and use control flow linearization to remove the redundant branch. In Scooty, we eliminate the secret-dependent control flow in a similar way. We execute all the paths and keep the result from the desired path. However, unlike linearizing integers in cryptography libraries, we also need to handle arbitrary data types. So this brings us back to sorry for that. This brings us back to the technique challenge 2. Transformation must be able to handle arbitrary data types. For example, in a simple service function, one variable can be object, integer, string, noun, or undefined in different branches. So we extend the control flow linearization to enable linearization of accesses to references and objects. Here we have a key assumption that the metadata of the secret, like size and type, they are not secret. So for references, the linearization is just like linearizing integer. But for objects, the linearization will iterate through the entire object and merge each byte of them. After solving linearization for arbitrary data types, we also need to think about how to hide the access pattern for arbitrary data types. Here comes our challenge 3. In prior work, we convert a single array access to accessing the entire array. It becomes really inefficient in complex data types. So for example, if you have a try implementation of an autocorrection dictionary containing 1 million words, originally the runtime of a lookup is just all size of the word, and now it becomes all size of the try, and it's 1 million in this case. For now, our solution is still to simply access all the elements of an object, but in the future, we plan to revisit the obfuscation techniques like ORM to adopt it to provide a probabilistic guarantee, then reduce its runtime overhead. We currently have a partial implementation of CT transformer and CT interpreter. Now it supports 60 out of 176 E8 bytecode instructions, covering basic register, arithmetic, some comparison, and control flow operations. We manually verified 48 of them, have source code level secret-dependent instruction handler, and we also manually transformed one of it, the getKey property instruction handler, to be constant time. So now, when accessing an object property with a key, Scooty will access all the elements of the object. For evaluation, we currently have two micro benchmarks, select and indirect call. The select function takes a secret condition and a public value. It returns the public value or undefined, depending on the secret condition. The transform version converts it to a branchless selection. And the indirect call function takes a secret index and execute a function of the index in a function list. So this transformed version converts it to a for loop of function calls. We show the transformed version of the in source code, but the real transformation happened in bytecode and assembly level. We evaluate these two micro benchmarks with three configurations. First, the baseline setup, which execute non-constant time bytecode with non-constant time handler. And second, CT bytecode only setup, execute constant time bytecode with non-constant time handler. So the light gray bar here shows the additional overhead on top of baseline due to executing constant time bytecode. And third, the CT bytecode handler setup executes the CT bytecode and CT handler. The dark gray bar shows the additional overhead of executing a CT handler. So for these two benchmarks, Scooty introduced 8% and 64% overhead respectively. It's worth mentioning that the overhead vary from programs and the size of the object a lot. In the future, we first plan to adopt ORM-style techniques into V8 memory management. And second, we plan to provide a composable formal proofs for the overall constant time execution. And we also plan to evaluate Scooty from both security and performance perspective in real-world applications. And last, we also want to consider the secret leakage during transient execution. In summary, here we present Scooty. It provides cache timing side channel mitigations for serverless applications. Scooty modifies V8 engine to support automatic constant time transformation for JavaScript applications. And our solution can be generalized to any other language runtimes. That concludes my talk, and I'm happy to take any questions.
Okay, we have time for questions. Yes, Katalin.
This is very ambitious work. So I have a few questions. One is, what do you think is an overhead that the kind of developers would be willing to accept in this space? Like you mentioned 60%, would that be something that you could imagine plausible or not?
No, for developers, to be honest, I guess they won't accept the overhead above 10 or 20. I guess that's probably the maximum overhead they would like to accept. But for this work, currently we don't have introduced any annotations for secret or refined secret. So for general applications, I think the performance highly depends on how the developers provide the annotations for the secret they really want to protect. So this will affect the performance a lot. And probably in the next step, we could provide a more fine-grained type system with different levels of privacy control for the developers to let them tune the performance and the privacy.
My second question, if I may, is with respect to proofs. Like you're applying this to like production V8 engine. Like, can one do proofs in that setting?
Yeah, that's a very good question because we do get stuck here a little bit because currently V8 has its C++ implementation plus some DSL turbo and some assembler to construct their handler. So what we currently can do is just simply manually modify that, and this could be quite tricky, I would say. So ideally, I think we can use existing tools to extract part of the V8 implementation into at least it's a static type language, and we already have working on transforming the C++ code to custom code. So that's one way we can achieve that. So take part of V8 out and using existing to do custom transformation for them. And probably another way is to pick another tiny implementation of JavaScript engine. Yeah.
I saw there was another question over there. In the meantime, Xavier, you can set up.
Hey, thank you for the nice talk. I really like the setting of the problem you address. I'm curious a bit about how feasible it is for an attacker to do the kind of attack you presented in a real-world setting where there are many serverless applications. How easy it will be to target a specific application or to get secrets? Is there any analysis on this, like a study or a benchmarking?
Sorry, just to confirm, is your question about how practice is the current, like the ability of the observatory? Yeah. So first, we do have practical attacks in noiseless environment in cloud. That is, I guess, 2015. Showed the last level cache side channel is practical. Though for noisy environment, currently, I guess a lot of researchers are working on that, but technically, in practice, it's not very feasible. However, I think from security perspective, we would like to have a solution even for theoretical attack. We don't want to be just find this is really practical, but we don't yet have a solution. So, yeah.
Thank you.
Okay, then let's thank Yao again.
Yeah, and then you could just put in your pocket something with the antenna sticking out.
Should come. Worked before.
Gotta trust it.
Yeah. Whatever. Okay. Perfect. So it's
Great.
Yes.
Okay, then for the second talk of this session, Xavier Fabian from CISPA is going to talk about lifting security properties to stronger attackers. Go for it.
Thank you very much for the introduction. Yeah, I'm Xavier Fabian, and this is joint work with Marco Guarneri and my advisor, Michael Backes. So before I can start with the real interesting stuff, I need to first give you guys a little bit of background about different kinds of things like spectre attacks and how we can model those for compiler countermeasures. So first of all, what are spectre attacks? Here's a little code snippet where we have a bounce check essentially, where we check if this index is in the size of this array. And because of modern CPUs use like different kinds of speculation or predictions to predict the outcome of those branches, because that's actually faster than just waiting for the result. It can happen that those branches actually mispredict. We execute this code on line 2 and line 3 with an index bigger than the size of A, thus we get a leakage. However, what's actually happening is that the architectural state of the program is rolled back, but somehow microarchitectural details, for example, in the caches still remain, which can be read by an attacker. So in general, those spectre attacks exploit hardware mispredictions to leak confidential information. And actually, there are a lot of different kinds of such spectre attacks, like we saw seen conditional branch prediction, indirect jump prediction, return prediction, store prediction, and
branch type prediction. So first of all, what we want to have is we want to have a model for those kinds of speculative primitives, for such speculative semantics. And for that, we use contracts, which are labeled transition systems. And we can split them up into two specific parts, the observer mode and the execution mode. Here, the observer mode, tells us what kinds of observation the attacker can see during the execution of our program. This, for example, accounts for like load observations, store observations, and the program counter. And the execution mode tells us what parts of the program the attacker can actually observe. In the simple example we've seen before, we had this like if misprediction, so these red full circles represent the mispredicted path of the program, and then the green circle represent the correct path of the program. Now, we use like this little scripted C for that with like a superscript, which we call CT for the constant time attacker for the observer mode, and the execution mode is in here marked with this X. And for the remainder of the talk, we really fix this attacker, this observer mode that we have to the constant time attacker, so we just leave it out. Okay, cool. So now we have a model for the speculative attacks we want to have. Now let's look at countermeasures, and in this case, compiler countermeasures. There are like stuff like fences, something called a red poline, speculative load hardening, index masking, for those different kinds of speculative contracts that we have. And of course, we want to also investigate the security argument of these countermeasures. So let's first formally define what the security would be for such a compiler. And here we use a notion called RSNI for robust speculative non-interference for a program. So a program is RSNI for a specific contract if it does not speculatively leak more than the non-speculative execution. And similar, we can then lift this to compilers. So a compiler is secure for a specific contract, so RSNIP for robust speculative non-interference preservation, if it of course does it for all of the programs. Okay, now with the setup, well, we can investigate the security of our programs, where we can investigate if those compiler countermeasures are secure. So we can select certain compiler countermeasures. We can select fences for this speculative contracts on branch misprediction, on indirect jumps, like a red poline, and so on. And this looks nice, right? But, well, there's a reason why I left so much space there. Namely, the problem is, right, I said in the beginning that these kinds of speculative primitives that are used in the CPU, they're actually used at the same time. So, well, it's nice to look at the single versions of those kinds of things. We really need to look at the whole picture of it. And we need a way to somehow reason about the security of the programs to such stronger attackers, especially for those countermeasures. And maybe one thing you can come up with, like when you see this, is as a first try, where we can say, we have a compiler that is actually secure for this contract CY, and you take a program that is secure for that contract CX, and then you somehow lift this right to this combined contract, where you compile that program to gain the security of both of the sources. However, this actually does not really work, right? That's a little bit problematic. And let me give you guys a concrete example for this. In this example, we look at this compiler countermeasure called red poline, where we have a very simple program that just does an indirect jump to this AIX register. And this red poline sequence replaces this indirect jump by this like huge blob of code. What this does is essentially saying, we start at the top, we call this thunk. This thunk then calls this lint1 label, where we move this AIX register into the RSP, which is where the return address is stored, and then we do a return. So then we could argue for that contract that speculates on indirect jumps, this CJ contract, if this is secure. And well, for now, it's, I think, enough to say, there are no more indirect jumps in the code after you do this transformation of the code. So yes, it's secure. But when we look closely at this code sequence that we've generated for this indirect jump, we can see that we inserted a return instruction into the code. And we have certain speculative primitives that also work on return instructions. For example, this contract CR that works on return instructions using another microarchitectural detail of the CPU. And also there's another contract that does it similar. So what maybe have happened here is, right, we had this initial program that was secure for this contract R because there were no returns. We modified it with this compiler that protects us now against this contract CJ, but we may have reintroduced new vulnerabilities into the code after the program transformation. And this is very important, right? Because when the compiler developer developed like these countermeasures, he may have only had this one attacker in mind, for example, here in this case, this CJ, but didn't like think about the other kinds of speculative primitives that could happen and that could be abused in other cases, or even there may be new spectral attacks that could be found. And this is what we somehow now want to capture, right? We want to capture when we have a compiler countermeasure, how can we say, does it break other contracts or does it not break other contracts? And for this, we came up with the notion of a well-formed translator. And we say a compiler for a contract CY is a well-formed translator for CX if it satisfies two conditions. And let me guide you through this, right, because now we have two contracts, so it's a little bit heavy. First of all, we have this notion of what we call security in source, where we say that compiler should really work for that contract CY. So we actually have a secure compiler. Now we come to the more interesting fact, which we call independence, where we say that if a program was secure for a contract CX, which is a different one than the one for CY, and we compile that program now with our compiler that actually works for this contract CY, then what we should gain is that this compiled program should not lose the security for that contract CX that it was initially secure for. What this means is then, right, we did not reintroduce new vulnerabilities into the code during the compilation that would allow an attacker to abuse it for this contract CX. And with this, we can now define, like after our first try, we can say we have this additional condition that our compiler is a well-formed translator, so we have this notion of independence for that contract CX, and we have that our program is actually secure against that contract CX. Then we can now really lift it to that combined attacker, this contract CXY, when we compile that program. So we solve that problem that there may be bad interactions happening after the compilation. Okay, now let's go back to our example, right? We had like this return instruction, so we may now want to prove this like well-formed translator, and we do this in this concrete example for our red polyline compiler that is secure against this contract CJ for speculation on indirect jumps, and we want to have it as a well-formed translator for this contract R that speculates on return instructions. So first of all, the first thing we needed to prove is the security in source. So that I already told you guys about. We remove all indirect jumps, so there's no speculation anymore for this contract CJ. Now, of course, we need to prove this independence notion for this contract CR. If we have a program that actually was secure in the beginning for that contract, our compiled program should as well. And intuitively, this works because there's like this middle blob of code in the red polyline I did not say anything about, right? Which in this kind of return speculation that happens on a return actually traps the speculation inside this little loop here, right? Where we have a pause, we have a fence, and then we jump to this label 0, which is then a self loop, which then traps the speculation, and after speculation is pulled back, we just return. So yes, we can argue for that kind of case that actually it is independent, and it's reasonable to apply it. And then using our corollary, we can then say for a program that is secure for that contract, we can lift this to the stronger attacker for that combined contract when we compile that program. Okay, that's very interesting. And what we've realized is as well that if we take, for example, another compiler, in this case, a compiler that inserts fences after every branch instruction into the code. So here we look at a contract that models speculation on branch instructions. We can prove this secure as well. And of course, well, we may want to prove independence with respect to another contract, maybe the contract on indirect jumps. And of course, then this means, well, you need to prove really this independence statement. But what you see in the compiler is really where you only insert like fence instructions into the code, and can those fence instructions that this compiler only inserts really have bad interactions with the indirect jumps of this other contract that we have? Not really, right? So we came up with another notion called syntactic independence, where you take the instructions related to speculation of that contract, in this case CJ, which is just a set jump, and you take the instructions inserted by the compiler, in this case those are only fence instructions, where what you see is where there's no overlap between those. So when this is empty, we can say that this compiler is actually syntactically independent with respect to this contract B, and in this case this contract CJ, without needing to do a proof of those independence that we have before. And of course then what we have is that if our compiler is syntactically independent, we can show that it also implies independence for that statement. Now if you go back to our picture, we now have a way with this notion of independence and syntactic independence to lift the security of the programs to stronger attackers. And in this case, for our wet-poline example, indicated here, we can actually show that we can go like up to the top of that little lattice that we have by showing in this independent statements for those different kinds of contracts that will lead us up the lattice, essentially. And interestingly here, we can see we can only reach a half of the lattice. And this actually has to do like this other version called SLS, which has also does speculation on return instruction, is actually vulnerable after applying this wet-poline countermeasure. So we cannot show those independent statements and thus cannot compose it together with the security of other programs. So yes, that's it. Thank you very much.
Okay, we have plenty of time for questions. Yes, Kathleen, the assistant, maybe, or maybe I can give you mic.
Okay, so very nice work. Yeah, so my question is, do you have, have you explored also other paths that would reach this, what seemed like a stronger or a different security property at the top?
You mean like going the other half of that tree?
Yes.
Yes, yeah. If you use other compilers, you can reach that as well, for example, using fences. Of course, right, if you only want to use fences, if you think about performance, that's maybe not the optimal way. But yes, you can do that as well. And yeah, we do that for a lot of compilers. We try to check, what is the strongest independence property we could show.
Cool, thank you.
Maybe also a quick question, since you're on this slide. There is no top in this lattice. Mm-hmm. Is there like a hopper to get there?
Yeah, that's actually a limitation of how you can combine those contracts. It's right now not possible to combine two such speculative primitives that speculate on the same instruction, which would be the case if you want to combine this like R and this SLS. That's why there's no top element right now of the lattice. But in the future, I think we want to lift that restriction to allow for both kinds of speculation on return instructions.
Mm-hmm.
Also, if you look at other properties that are not speculative based, also if you look at other properties that are not speculative based, there might be a top. Like if you think about cost and time, which is generally requires memory safety, you can imagine a lattice like this where memory safety is lower and then constant time is higher, right? And then you can have speculative constant time, which is higher again. So in the case of speculation, we don't have a top, but in the other cases, for other security properties, that might be.
Got it. Thanks.
Yeah, maybe I should also mention that's really a lattice, so there's really a partial order between those contracts. So there's stuff you can do there as well, exploring different kinds of properties for compilers.
More questions? Yes. So how difficult are these proofs? I guess syntactic independence is very easy, but are there other cases that are more difficult?
I think proving this independent statement for the sweat line example is a little bit more involved, right? Because you need to argue that that return instruction is actually trapped. So that can be more involving, yes, in those cases. But it's still doable. So it's, yes.
Half of those are secret compilation. Like, can you scroll back to the...
I can run. It's still young.
Yeah, I mean, if you want to prove that something is a well-formed translator, well, you also need to prove the security of the compiler.
Right.
So
Like, Catherine, rsnip is really an instantiation of like RSC. So it's a kind of, yeah, it's a journey beyond full abstraction kind of proof. Back translation, all that stuff.
Yes.
And do you have like a uniform way to do this proof? Because I guess they might be pretty similar, right?
Yeah, that's true, yes. So, yeah, there's like, yeah, it's a uniform way, you could say, yes, on how to prove those things, which also come from this exercising spectral work, where we can then do that for those compilers as well.
We have time for one more question while Matisse set up. If not, let's thank Xavier again.
Yeah, if you just want to click that somewhere down on the top. And then just stick that in your pockets with the antenna stick.
Okay, all set. Then for the next talk, Matisse Cruz will talk about composition of spectral mitigations. Go for it.
Okay. Yes. Hello, everyone. As introduced, I'm Matisse, and I'm going to talk with you, or to you, about the secure composition of spectral mitigations, which is joint work with Professor Michael Backes. So, well, you've seen it one talk earlier, but for sake of self-containment, let's refresh ourselves about this speculative execution example. So we have a simple bounce check program and some kind of array access that uses this index, right? Now, if you suppose that that index is, for example, 1337, and the size of the array is actually just 64, well, then clearly the bounce check is false. However, bounds are, or branches are typically rather slow to execute, so modern processes do speculative execution, and you would speculate here on the fact that the condition is actually true, and start to actually load the value that is at that particular position. So clearly way out of bounds and just some random garbage. And well, at some point the processor may notice, well, okay, that guess that this branch is actually true was wrong, and roll back. And so this rollback operation, unfortunately, is done in a dirty manner. Stuff is left on the cache, which an attacker could exploit. Okay, so much about that. You can, for this particular example, introduce a barrier operation. Which just says, okay, if you start to speculate, then just stop here, right? Just stop
speculative execution, and wait. So there is a mitigation technique to overcome certain speculative execution vulnerabilities, and there are many such vulnerabilities, and even for a single vulnerability, there are a plethora of other mitigation strategies. So I've shown you this strategy where you just insert a barrier, but it's a very slow strategy because you just say, okay, just don't speculate at all. But speculation has been introduced to, well, improve performance. Clearly not necessarily the best strategy. And also we may be interested in, well, I mean, this is a big graph, right? And we do formal methods. And typically you are interested in doing this in a kind of modular fashion. If you tackle this globally, if we have like one compiler pass, for example, that makes sure that there is no speculative execution vulnerability that does this in a monolithic manner, then this is clearly not so desirable. And also in practice, compilers are developed in a, I guess, modular fashion. So if you have a very simple compilation pipeline where you start with a blue program and you would translate this to a kind of, in this case, intermediate representation in red. Of course, in practice, you perform some kind of optimizations, analyses, all this funky stuff. And at some point, you lower to your target language. And from my point of view, or from this talk's point of view, these compilers are just compositions of smaller compilers. So we can view a compiler as several smaller compilers put together. And well, if you now consider that maybe this one, this compiler A and this compiler B are secure, one question would be whether the resulting pipeline is secure again. And unfortunately, this does not necessarily hold in general. So one example of this is as follows. Let me first give you an example where we have a desirable compilation pipeline where it works. So here we have a read operation at a particular memory location and some particular index, which is potentially out of bounds. Now, if we have a compiler that introduces bounds checks, we would introduce a bounds check for each memory operation. So again, a very stupid countermeasure because we could optimize this somehow, but for the sake of this example, we introduce a bounds check for each kind of memory operation. And in this case, this bounds check is again false, and we again have the speculation with a potential leakage of the value. Now, if we compile this program further using this barrier compiler that just introduces a barrier after each branch operation, right, completely disabling speculative execution that way, we essentially end up with a program trace that does not contain the leakage because we have the barrier when we start this speculative execution. So we end up with a secure program, at least with respect to that particular kind of speculative execution vulnerability. However, if we now swap these two compilers, so if we first introduce barriers for each branch and then introduce bounds checks, we are kind of screwed in the sense that the bounds check compiler introduces the bounds check, but this branch is now not secured with a corresponding barrier operation, right? So the compiler tried to enforce memory safety in that sense, right? To make sure that you don't have out-of-bounds accesses, but in doing so, introduced another vulnerability, which we don't want to have. Right, so the goal of this work, the goal of this talk is to provide a formal analysis of the compatibility of different kinds of these compiler mitigations, right? So first up, let's maybe refresh ourselves what a secure compiler actually is. And for that, I go a little way back and talk about correct compilers. And I'll make it quick, don't worry. So from the perspective of this talk, a correct compiler is just, this statement where you have a whole program execution at the target level, and essentially the compiler needs to preserve the property satisfaction. So we have any kind of property, for example, memory safety, and the compiler has to make sure that if that property holds in the source, it should also hold in the target. But clearly, compiler correctness in that fashion is not necessarily practical, because in practice you would write programs that are not whole, meaning they have holes, they have undefined symbols. If I write a simple C program that does printf, that reads from standard input, I need to link to the C standard library. So I rely on some kind of assembly blob that I link after compiling the C code to provide me with these missing definitions. And this is captured in the well-known robust preservation statement, where you just quantify over partial programs instead of whole programs and contexts which you link with this partial program. So this exists in literature, and this is our notion of compiler security for the sake of this talk, also known as robust preservation or robust trace preservation. Okay, now we've proven in earlier work that you can compose this actually. So if you know that you have a compiler that is secure, so robustly preserving a class of security properties C1, and you have another compiler that is robustly preserving with respect to a class of security properties C2, then you can compose them together, run them in sequence, and end up with a compilation chain which is secure with respect to the intersection of these two classes. But again, in practice, even if you have a very, very simple compiler, namely the identity compiler that just performs a recoloring operation, so we have very similar programming languages, the blue and the red are syntactically equal, however they differ in one way. The blue language does not have speculation at all, and the red language does have speculation. So even for a simple compiler that essentially does nothing, you end up with different traces in the source, or different trace models in the source and in the target language, right? For example, with the bounce check program, in the language, in the blue language, where I have no speculation at all, I would perform the bounce check, potentially see its faults, and that's about it, because there's no speculation. But in the target language, I would perform the speculative execution and have the leakage, right? So clearly, there needs to be something done with respect to the compiler security statement. And this also has been done already. So essentially what we want, for example, we have this property that we don't want to have any leakage whatsoever at the target level. And what we essentially want is to translate this to a source level property, or rather, if we already have a source level property, translate this to a target level property. So we have two kinds of functions that also are in a, well, form a Galois connection. And they are parameterized over a cross-language trace relation, where you say, okay, this blue trace should be equal to this red trace. And this really induces these kinds of mappings, where I can go from a red property to a blue property and back again. For the sake of this talk, we are only interested in this projection, where we go from red to blue. So from target level properties to source level properties. And we change the statement accordingly. So instead of having a black trace, now we have a blue trace and analogously a red trace. However, we also quantify over target level properties. And well, for the blue trace to, somehow you need to say, okay, this blue trace needs to be in the projected version of this target level property. And we've also proven that this composes. So if you know that you have two compilers that are secure with respect to certain security classes of properties, then you can compose them. The crucial bit is that the first compiler that you have in your pipeline, or like in this two-compiler pipeline, needs to be secure with respect to a projected version of the first property, which can I zoom? Yes, I can zoom. Nice. Which makes use of this relation that represents the semantic effect that the other compiler has. So the compiler that we run after the first compiler is run, right? And if we go back to the example where we first run the bounce check compiler and then the compiler that introduces barriers for each branch, then we remind ourselves that if we run it in this order, then everything is fine. But if we swap the order, then we get into trouble. And we get into trouble because if we want to make sure that the compilers, the whole compilation chain, is secure with respect to a property that says, okay, there should be no speculative leak whatsoever, at least with respect to that variant, then if we project this to an intermediate level property using this bounds relation that represents the semantic effect of the compiler that introduces bounds, meaning essentially equating this red trace with this green trace, then we are in a sense screwed, because we can find an intermediate level trace that is related to a target level trace that violates the property that we do not want to violate. And you have to make sure that this does not happen. So you have to make sure when composing that you cannot come up with an intermediate level trace that somehow is related to a target level trace which violates the property that you want to make sure to not violate, right? Yeah, so the overall goal of this work essentially is to make several proofs about compositions, about these compiler compositions for different speculative execution mitigations. So for example, if we start with a completely insecure program with respect to speculative execution, then we may apply the barrier strategy or this index masking that Xaver mentioned earlier to obtain a program which is secure with respect to the spectre variant V1. And I presume that you can apply index masking and the barrier operation again on a program that is already secure with respect to V1 and still obtain a program that is secure with respect to V1. And yeah, we kind of want to expand this graph further. If you now apply this barrier compiler again to make sure that the spectre variant V4 cannot be exploited, then I envision that in the end you get the combined version of V1 and V4, again can repeatedly apply the barrier operation. But for example, if you now apply the index masking, then the V4 variant may break, right? And so on and so on. So the final goal is to really, the final goal of this work is to really prove this graph, to make sure that, okay, I know really what compilers I can compose to end up with a secure program and to know what kind of security statement I have. So for example, I know that I can start here and just like go this path maybe. Okay. Yeah, that's already it for my talk. So thanks a lot. Do you have any questions?
Questions? Yes, Peter.
How many distinct subsets of protection do people out there in the world want to use?
That's a good question. I'm not a person that is out in the world, so it makes sense to make sure what subsets they are interested in, right? I cannot faithfully answer that, unfortunately.
So do I understand correctly that the goal of this work is rather similar to the previous speaker? And if so, can you compare? And
Sure. So we've done this composition framework in earlier work. And what we now want to do, which, we can use the earlier work for this work as well. But it differs in the fact that the framework that we have here is a little bit more generic in the sense that you talk about the composition of these compilers, and the earlier work was more focused on specifically speculative execution variants. Whereas here you could really have any kind of property whatsoever that is expressible by means of program behavior, namely events, sets of traces, and so on. Yes, and this is a mere instantiation of that framework, basically.
This work is really about composing compiler passes, whereas Java's work is a single compiler pass, how strong a guarantee can I get for that single compiler? Now, of course, there's synergy between the two, right? Like Xav's results can be reused in Matiss's results, and Matiss's results, in a way, they fulfill some of the well-formed composition assumptions that Xava needs. But there's one is for multiple compilers, one is for single compilers, for example.
I have a question.
Yeah.
Are you planning to use like a proof assistant to formalize this theory and compose things, or do you have any ongoing work on that with that?
Yeah, so parts of the existing theory with regards to the composition, or rather the core composition theorems, so let me go back to this one. Yeah, that one. That is formalized in COC or in ROC. However, of course, you need to provide a secure compilation proof for the particular compilers. And in order to instantiate this framework, you need this, or kind of need to assume this at some point. And there are not so many practically relevant compilers that are formalized in the proof assistant, right? So, yeah, it's somewhat open whether we can formalize everything, but I presume at least the core theoretical work can be formalized in core.
Right. So one thing that like I've always feared with respect to modeling speculative execution and proof assistant always like seemed like super hard to me. So like, it would be very cool like to have some of that, I think. Especially not only speculative, I would say, but in particular out of order. Yeah. Because I feel like you need to keep a lot of like the reasoning about like out of order execution. You need to somehow keep on the side a lot of invariants about, I don't know, like your configuration can still step and like, so yeah, would be interesting to see that happening. Dominique, one more.
So I'm curious how you see this fitting into a full compiler pipeline. So I guess this is the sort of thing that you would have to do all the way at the end, but I mean, is that feasible, because you still have linking going on afterwards, and maybe dynamic linking, and so which sometimes inserts weird code that does sort of lazy loading and whatever. And have you thought about that at all?
Yeah, I mean, in the end, it boils down to the question of how practical the robust preservation statements are in that sense, because the composition framework here really relies on them. And if you can model a practically relevant compiler and prove it to be secure with respect to these kinds of statements, then I think it's totally feasible. But of course, we don't really have like a really production-ready compiler that is formally proven secure with respect to this kind of statement.
Sure, but how do real compilers do this? Do they do this red Pauline, for example? Do they do that in the backend all the way at the end in the backend, or how do they prevent like very late optimizations from breaking the properties again? And
yeah, good question. From what I understand from the community that is interested in making sure that cryptographic constant time really holds in the end, for example, is that people still tend to insert inline assembly or like annotations that make sure that, hey, compiler, just don't touch this and just translate this one-to-one. And I guess people in the speculative execution community do similar things because there is an overlap between them, right? Both are likely people that are interested in developing cryptographic libraries, for example. But yeah, it's a bit outside of my practical expertise, to be honest.
Oh, a question there.
Oh, do you want to?
No, please.
Yeah.
So great talk.
Thank you.
Usually one of the nice things about sort of these vertical compositionality proofs is that you can do that proof independently of that proof, right? That secure compilation proof independently of that secure compilation proof.
Yeah.
And in this diagram, that's not exactly the case anymore, because now that little sigma over there, right, is somehow dependent on that second compiler.
Yes.
And I understand that's sort of maybe just an inherent difficulty in certain situations like this, but I'm wondering if there's any relationship between that the unadorned class C1 and the projected class with the sigma, like if I've already done the work of proving it secure with respect to C1, do I gain any benefit now when I go and I try to prove this modified class, or is it really like I'm starting from scratch? Or does that depend very much on what sigma is?
It depends very much on what the class of security properties is, and it depends very much on what the trace relation that sigma uses actually is. So sigma is a set thing that is constant, so to say, but it relies on this cross-language trace relation, which kind of is induced by the compilers that you use in your compilation chain, right? They describe the effect that the compiler does. For example, for the bounce check compiler, the cross-language trace relation would say, okay, I associate each memory access with a sequence in the target that says, okay, I have to do a bounce check first, right? And then potentially perform the memory access. So clearly there is some overlap, but I have yet to really get into the details to see it, like in a concrete instantiation of this, how difficult or how proof reuse actually happens in that sense. Yeah.
Thank you.
Okay, let's thank Mathis again. Okay, great. So for the last talk of the session, Matteo Busi from Università di Venezia, Ca' Foscari, will talk about obfuscating crypto code while preserving constant time. Take it away.
Thank you, Marco, for the introduction. I'll try to be fast because I'm standing between you and lunch. And, well, this is actually, hopefully this works. Yeah. This is actually started as a kind of side project, fun side project to learn more about coq/rock, and then it's quite interesting, so we submitted. It's still a work in progress, so I will tell you where something is not still finished. So let's start, and well, I had this slide because we presented this somewhere else, and people were not secure compiler guys, so compilers. What's a compiler? A compiler is a function well, it's actually for us seen better as a composition of some transformations that map some source language into a target language, and we would be happy, very happy, if this compiler preserved some functional properties like correctness, so for instance, think of CompCert, and non-functional properties like cryptographic constant time or hyperproperties, robust hyperproperties, whatever. So this is more or less the setting, and we started with a very narrow question. What if we take a single program transformation, actually a class of program transformations, and we proved that they preserve some property of interest? And for us, the choice was, well, maybe let's take a look at program transformations that are relatively simple to like formalize or to characterize, and which are not well studied. And the choice went into program obfuscations, which are actually well studied for correctness, well, some of them at least. But as far as we know, there's not much about their preservation of security properties. And the property of interest is cryptographic constant time. Again, this is very well studied. We have a lot of formalization to start from. And the idea of cryptographic constant time is to defend the program against some intruder that observes I/O operation of a program and its, let's say, running time, the time that takes for the program to perform some operation, for instance, cryptographic operations. And observing that behavior, an attacker can actually discover some secrets, for instance, keys. And sorry, I didn't tell you what a program obfuscation is, actually. It's like a program transformation that scrambles up your source code and actually changes the data flow or the control flow of the program, making it hard to reconstruct the original information. Actually, this is precisely stated in some sense that you can think of it as a program transformation that when you try to analyze the target program leads your analysis to reach top very fast. So in the abstract domain, it reaches top. This is a possible formalization of that. And you may wonder, well, I don't know, why should I obfuscate cryptographic code? Well, actually, we really don't know. It looked like a fun project, but it actually may have application to white box cryptography or the deployment on the web of programs like minification can be seen as a kind of obfuscation. So let's go ahead and let's see an example, which is pretty standard, which is mixed Boolean arithmetic. And that takes a program, which is this if then else, for instance, that has a few expressions like this comparison here and this assignment here, and that it obfuscates it using this nice property of the plus operation that tells you that you can rewrite this plus operation as a combination of plus some bitwise operations. So for instance, this one can get transformed to this one, and this x plus y gets transformed in this way. This is actually there's actually a class of these rewriting rules, which is quite well understood for finite fields. And that's it. It may not be trivial that this is correct, but this is actually working for for integers, so finite fields. So we saw an example of an obfuscation. Let's see something a bit more concrete about cryptographic constant time. And the thing is that we consider there are a lot of different definitions for this property. We consider this definition, which is pretty much standard in an imperative setting, with an imperative language, which is actually memory safe, with array and pointers, which is inspired by a core of Jasmine, which is a well-known programming language, well, for cryptographic code. And the cryptographic constant time is just another termination insensitive non-interference. And it tells us that if we take a program P, we run it on some low equivalent memories, and if this program terminates in both memories, then the leakage that the program produces is the same. So a bit more formally, we can write it like this. I don't want you to read all that, but the nice thing is about this leakage here that you can see. If both program terminates with some leakage L and L prime, then they end up having the same leakage. And this leakage is actually, well, I want to go into details, but that's a structured leakage in many cases. This is inspired from previous work in the literature at CCS 22, if I remember well. And L tracks down the operation that happens in P. So memory operation, which we call them memops, which are array and pointer location, but not their actual values. And the results of guards/condition evaluations for each, for instance, on if then else's and while. So that's more or less the setting. And now we can talk about preservation. You all know about preservation. So the preservation of this property here, which is cryptographic constant time, is just if P is cryptographic constant time, then its compiled counterpart, which I will never write the compiler, I just write the pink program, is CCT. There's a nice remark, which is, I guess, clear in this community, but apparently not everywhere. An obfuscation may actually increase the leakage, but since we are looking for a non-interference, we are just interested in comparing the leakage intra-language at the target level. So if they were the same at the source level, then they must be the same at the target level. But nothing guarantees us that at the target level, the leakage is the same as the source, or is less than the source, whatever less means. So our idea, since particularly Pierpaolo is very fond of static analysis, was, well, can we do something statically to check that? So without relying on some semantic properties of the programs. And the answer is apparently yes. I will tell you in a while why apparently is the keyword here. And we need two additional definitions. So consider this this program, which is as simple as an assignment to x to 0 and then an if then else, a generic if then else, with a guard and some comments. This gets obfuscated to this thing here, where the x equal to 0 gets obfuscated as a while loop that decreases x with some guards, decreases x up until x is 0. So this guard checks if x is 0 or not, and exits the loop. Here we would like to look at top-level expressions, which are circled here. It's a kind of a strange definition, but for the sake of this talk, this is a top-level expression, x is not. G is a top-level expression. C1 and C2 are not expressions, so that's fine. G prime is an expression, G is an expression, and x minus 1 is an expression. And on top of that, we magically build this correspondence M, which maps, let's say, target level, top level expressions to their source level counterparts. So, yeah, so G is mapped back to G. X minus 1 is mapped to this star thing to denote that this is new, and G prime the same. Of course, we don't actually notice that we don't actually use syntactic equality. I mean, this is a case, but we don't require syntactic equality because this is kind of more at the semantic level, and it depends a lot on the obfuscation. So that's where the, let's say, magic happens, and we will probably require this M to be generated by the obfuscation, but we don't know yet. So our preservation check is now ready to be revealed, and it goes as follows. It's very simple. If the correspondence, so the function that tells you the correspondence between the source and the target, tells you that the expression is new, this star, then we require that the memory operation of the expression is empty, or this expression, if this expression is a condition, we require it to be a tautology. Otherwise, if this is not new, we just require that the memory operations, the memops, are preserved across the transformation. And yeah, here is a big thing. Deciding if an expression is a tautology, of course, is hard. But often, since we know how this obfuscation is built, often we already know beforehand if this is a tautology or not. So this is kind of a trick. So our conjecture is the following. If P is CCT and it passes, and the obfuscation together with P passes our preservation check, the one that I just showed you, then its compiled version is CCT. And, well, we actually wanted to prove that in coq/roc. And I thought at the beginning this was like an afternoon task, but in the end, it was not. I'm working on it, still working on it. And this plus some additional reasoning on the form of the transformation tells us when a program obfuscation is safe to be used in any case. And this is actually very trivial. So if this transformation preserves CCT, if for any P this satisfies the preservation check. And well, this is trivial, of course. And well, so let's go back to Big's Boolean arithmetic. We have this example here. And as you can see here, these expressions, this box here and this box here correspond through M to this expression here and this expression here. And as you can see, the MBA never adds top-level expressions, because it's the way it is defined, and uses the obfuscated expressions, in the obfuscated expression, the same operands from before. It just changes the operations. So it adds no new memory operations, and so MBA is always secure. It satisfies the corollary from before. So we are very happy with that. But of course, more, let's say, complex obfuscation do not preserve CCT. So for instance, we have this anti-taint analysis from Tigris, which is an obfuscating source-to-source compiler. And it obfuscates the data using control flow, the example I showed you before. So this assignment here, an array in position 3 is assigned to 0, is obfuscated as this while loop. And, well, this new guard here has a non-empty memop. And since this is not empty, the check fails. And so CCT might not be preserved. This is a bit imprecise because actually this has to do with the fact that this is a while loop and not an if then else. Because if this was an if then else, this would be good, and we would have a false positive. But yeah, that's a static analysis, so that's okay. And however, what one can observe is that sometimes for the same obfuscation, we get secure programs. So we can go a program by program basis, and for those of you who know me, I love this translation validation stuff. So instead of doing that once and for all and doing like on every possible program, we do that program by program. And for instance, this is an example where the same transformation as before is secure because it never operates on memory, so this is trivially secure and no problem. So, concluding, we started with the idea, very simple idea, much less ambitious than previous talks, and of having one classes of program transformations and against one property of interest. And we show that a simple static check shows when a obfuscated program is still CCT, and if this check works for every program, then we have some suggestions, some guidelines. We can compile a list of transformations, obfuscations that are always applicable, so they are safe to apply, like MBA. However, if the check fails, we can still do something, and we can follow a translation validation approach and go case by case, and well, we are happy. In the future, we are, well, actually, yeah, in the future, because this should be the current working program, but I'm still stuck in the proof. So in the future, we would like to embed our static analysis in obfuscating compilers. Like we initially thought of Tigris and OMVLL, but some of the reviewers suggested LLVM obfuscator. So thank you, the reviewer, if you are here. And we are looking into that. And also maybe in the future, this could be very interesting to have more transformation and more properties to make the thing a bit more interesting also outside the specific fields like white box cryptography and stuff. And that's it. Thank you for listening. And of course, I'm happy to take any question.
Okay. Yeah.
Hi, thank you for the talk. And I have a question. I'm a little bit unsure that is the instruction pointer IP is part of your leakage model, or it's not?
Wait a second. Not really, because we are at a higher level than like low-level languages. But in some sense, it is, because we track conditions on while loops and if-then else's. So you can reconstruct it. If you want to have an instruction pointer, then you should be able to do that, I guess.
And you can also apply obfuscation on that.
Sorry?
Can you also apply obfuscation on your IR accesses? Sorry, IP accesses? It's a random question.
I don't know. Actually, I guess. But yeah, you can, because this actually works. I didn't show here, but it actually works on control flow flattening, where you actually explicit your program counter. And so, yeah.
Yeah, I see. Thank you.
Another question there.
All right. Thanks for the talk. So that might be a bit of a naive question, but the way I understand it, constant time programming is used against timing attacks, right? But from your definition, I don't see where the timing would come from, right?
Yeah.
It seems to me you're more doing an observational determinism kind of property. So how would that work? How would you give guarantees about timing?
Yeah, because this is not. Can you hear me? Yeah. This is a more of an abstract model of cryptographic constant time, where this is pretty standard in programming languages. There's a paper about. There are a few papers about that, but yeah. Give me a second. Yeah. Here, when you track memory operations and the conditions of loops, then this is I would say, an abstraction of what happens at low level with cycles. So you can reconstruct that information. Well, sorry, not exactly. This is an over-approximation, I guess, of what's happening at the low level with timings.
Okay, but just maybe as a concrete example, you have this obfuscation as a while loop, and if it's not memory dependent, you say it's trivially okay. The one with x equals 0 gets obfuscated. As
this one.
Or the one that you had at the
at the end, right?
Exactly the next one. So this one you say is unsafe, right? But if you go to the next slide, right? In this case, let's say if x before had my secret key, right? Basically, the timing of how long the loop runs is gonna leak information if I can measure that. Right?
Yes, but not in this model, because here x, you can think of it as a register, and in this model, I haven't shown you, but this is actually a non-interference, right? So here x and like other names are, you can think of them as low parts of the state, and this is fine if you leak them.
But I mean, you can load like a secret from memory, and then it ends up in a register.
Yeah, but in that case, that wouldn't be good. I mean, if you swap this one, like x equal to a3, then you keep track of that. Okay. You can think of it. I mean, it's like a taint analysis for information flow. That's the same thing.
So like your obfuscator does not allow secret conditions.
Yeah, exactly. Yeah, that's the typical cryptographic constant time policy that they use when they program cryptographic libraries. They don't care really about time, but they do care about this abstract model that allows you to say that there are no timing problems.
Thank you.
Any more questions? If not, let's thank Matteo again. We have a lunch break now, so we reconvene at 2. See you later.
Okay, I got the authorization to start. So welcome to the third session today. The first speaker is Dan, who is going to talk about compiler support for control flow linearization using architectural mimicry. Please go ahead.
Good afternoon. My name is Dan and I'm a PhD student at Distrinet at KU Leuven. And I would like to present a compiler-based defense against side channel attacks that makes use of a novel hardware defense called architectural mimicry. Before talking about our compiler defense, I'll give a short introduction on microarchitectural attacks. And then I'll explain how to linearize control flow, after which I'll talk about how we implemented this in LLVM. Finally, I'll discuss some experimental results. A microarchitectural attack is an attack where an attacker tries to get information about some secret data based on microarchitectural state that's shared between the attacker and his victim. For example, an attacker might be able to figure out if a branch was taken or not based on timing differences or other updates to microarchitectural state, which could leak a branch condition. Another example is the leakage of memory addresses through cache state. But with our defense, we focus on eliminating leakage through control flow. So the example on the left. And one way to defend against such attack is to make the side channel leakage independent of secret information. We assume the common constant time leakage model, where memory addresses are leaked by load and store operations, and secret dependent branches leak their branch condition if the execution time or other microarchitectural state is different depending on whether the branch was taken. And under this leakage model, we need to eliminate all secret-dependent branches by linearizing them. And the state-of-the-art method to linearize is to execute both branches and then use some kind of constant time selection primitive to discard the results of one of the branches. But this comes with some overhead, especially on architectures like RISC-V, where there are no dedicated instructions that could be used for constant time selection. This is where architectural mimicry comes in. Architectural mimicry, or AMI, is a new hardware extension developed by my colleagues at Distrinet, which provides new ways to balance and linearize code. They implemented this as an ISA extension to RISC-V. And it introduces a new execution mode called mimic execution, in which instructions have the same microarchitectural effects, but some architectural effects are suppressed. For example, a load instruction in mimic mode will load from the given address and touch the same cache lines, but it won't actually store the result in the register. Different instruction qualifiers can be used to control the mode of execution. By default, instructions have the standard qualifier, which means that they are executed normally in standard execution mode and mimicked in mimic mode, but the behavior changes if the instruction has a different qualifiers. For example, a persistent instruction is always executed in both modes. And this is a basic example of how we can apply AMI to linearize a secret-dependent branch. We replace the branch with an activating branch. This means that instead of jumping to the target location, block 3, we will instead enable mimic mode until that block is reached. And then always continue the execution at location 1, regardless of the value of the branch condition. So in this example, we'll always jump to block 1, and in the case that instructions at location 1 and 2 are mimicked, the value in V won't be affected because mimic mode is enabled. So that way you get the same behavior as the original program on the left without actually jumping to a different branch. You always observe the same microarchitectural effects. Unfortunately, the authors of AMI don't have full compiler support. They only provide an assembler. So all transformations to the code have to be done manually, which is quite tedious. Furthermore, their programming models assume structured control flow graphs, like the one on the previous slide, but it doesn't, their programming models, they don't generalize well to other kinds of control flow that you would commonly encounter during compilation. With these limitations in mind, our goal is to automate control flow linearization of reducible control flow graphs. Here are some examples. On the left is a structured control flow graph, which consists out of these nested if-else constructs. And that's the only kind of control flow graphs that their original programming model supported. But compiler optimizations often transform control flow graphs, such that it's no longer structured. And the term reducible is used to describe control flow graphs for which loops can easily be analyzed. And here is an example of this on the right. Which brings me to our main contributions. We've generalized programming models to support reducible control flow, and then we extended the LLVM compiler with support for control flow linearization. And then finally, we also evaluated our implementation on a few micro benchmarks and compared different approaches. The method we implemented is based on partial control flow linearization by Moll and Heck, which was introduced in the context of SIMD, but it can also be applied to mitigate against side channel leakage. And this method can be used to linearize any reducible control flow graphs, and we can adopt this method a bit to make use of AMI. So let me show you how this works with an example. In this reducible control flow graph, we assume that block 0 has a secret dependent branch and that we need to linearize. And we also assume that we have a compact topological order of the blocks, shown by the numbers on the blocks. We start by visiting block 0, and we first linearize this branch by removing a control flow edge to block 4 and replacing it with an activation of mimic mode. This means that we'll unconditionally jump to block 1, and depending on the branch condition C, we'll enable mimic mode. And mimic mode will remain active until block 4 is reached. But to make sure that block 4 will always be reached eventually to disable mimic mode, we need to make sure that all paths that start in block 1 eventually pass through block 4. So that's why we add a deferral edge from block 1 to block 4. And that's a kind of a temporary edge that we used to remember that block 4 must post-dominate block 1. Then we visit block 1, which we don't need to linearize because it doesn't contain a secret dependent branch. So we simply shift the deferral edges to its successors to maintain this post-dominance relation. When visiting block 2, things get a bit more tricky, since in this case, the deferral target is block 4, and block 4 comes before the successor, block 5. So in this case, we have to make sure that control flow goes to block 4 first. Otherwise, we're too late and we'd still have to go back to block 4 after going to block 5. So the deferral edge now becomes a new control flow edge, but we don't want to change the behavior of the program by introducing new control flow edges where there weren't any before. So to do this, we can make sure that this newly added edge is only taken in mimic mode. So that's why we can enable mimic mode in block 2. This means that if we're executing block 2 normally, mimic mode is always enabled before moving on to block 4. But if we are mimicking block 2, deactivating jump in block 2 does nothing, and we end up disabling mimic mode in block 4 because block 4 is the target of deactivating branch in block 0 that enabled mimic mode. The intuition behind this is that when we're in standard execution mode, we need to take the correct path according to the original control flow graph. But when we're in mimic mode, it doesn't matter what path we take as long as our path leads to the target of the activating branch that enabled mimic mode. So that way we can freely add any control flow edges without affecting the correctness of the program. Finally, we add a new deferral edge from block 4 to block 5 because we created the new activating branch. The next block we visit is block 3. Here the deferral target and the successor are the same, so we can simply remove the redundant deferral edge. The next block we visit, and then we can do the same for block 4, and we don't need to do anything for block 5. So now we visited all the blocks and we've completed the linearization of the secret dependent branches, which is only the branch in block 0 in this case. But in order for this transformation to be secure and correct, a few additional conditions need to be satisfied. To be secure, standard execution mode should be indistinguishable from mimic mode. This means that inside the secret dependent branch, we need to leak the same information in both modes. For example, we need to make sure that loads access the same memory locations, even if the results are discarded. And we can do this by using persistent instructions to compute the address that's being loaded from. These instructions are executed in both standard execution mode and mimic mode. However, an activating region is only correct if the live state is unaffected in mimic mode. This means that persistent instructions should not write to registers that are live and entering the activating regions. And this is why in the implementation we had to constrain the register allocator to make sure that those persistent instructions use free registers. Now I'll give an overview of how we've implemented this in LLVM. The first thing we implemented is the ability to mark secrets in C code with annotations using this annotate type attribute. The analysis and hardening passes need to be implemented in the backend of LLVM, so we need to propagate those annotations to the backend. First, we lower them into function argument attributes in the intermediate representation of LLVM. And then we need to lower them to machine IR, which is the intermediate representation of the backend. But to do this, we had to go through the selection DAG first before we can emit machine IR pseudo instructions. Now I'll give an overview of the hardening passes that we've implemented. So first there's a set of analysis passes that run. The first analysis pass is a taint analysis pass that finds the secret dependent branches based on those annotations. Next is a linearization analysis pass that determines a set of activating edges and new edges, but doesn't apply any changes. And the last analysis pass is a pass that determines which instructions need to become persistent instructions to ensure that branch conditions and memory locations are computed persistently. Based on this information, we prepare for register allocation by adding some constraints, which we do by inserting temporary instructions. Then register allocation takes place in which a physical register is assigned to each virtual register. And then we run the same three analysis passes I described before again. The main reason we did it this way is that it was a bit easier than trying to maintain the results of the previous time we ran those passes throughout the register allocation. But this isn't an ideal solution. And finally, we applied the linearization by replacing the branches and with activating branches and adding instruction qualifiers to the instructions that need to be computed persistently. Now I'll discuss the evaluation methodology and show some results. For the evaluation, we answered 5 research questions. Are the linearized programs still correct and secure? What are the performance results in terms of code size and execution time overhead? How do our different linearization methods compare to each other and to the manual linearization with AMI? And how does it compare to the related work? The general approach is that we run programs on Proteus, an extendable RISC-V core, and compare the execution traces that come out of it. We've only been able to evaluate our implementation on a small set of micro benchmarks, for which we have checked that the linearized code is indeed secure and correct. We find a code size overhead of around 6% when compared to the original insecure program. This is significantly lower than the methods that make use of conditional execution, where we find an overhead of around 55%. However, the manual linearization with AMI does slightly better and can achieve linearization with no overhead in most cases. Similarly, we find a 26% execution time overhead, which may seem high, but most of it is just a consequence of the linearization itself and can be avoided if we have to linearize. So since we need to execute all branch paths to ensure that we don't leak anything, for future work it may be interesting to implement a security type system in the front end in order to detect violations earlier, which should result in a much better programming experience. Furthermore, being able to express AMI semantics in the compiler backend would be useful to avoid needing these register allocation hacks that we've been using. But it could also increase the correctness and security guarantees, which are at the moment quite low. So since we can't really run this on larger programs yet, and one interesting area of research is contract-aware secure compilation, in which a hardware-software security contract would be used to communicate microarchitectural properties to the compiler. And lastly, formal verification of these methods could be interested, or implementing this method in a secure compiler. We have some time for questions left, I think.
So, questions?
Hi, I was wondering whether there is any formal work describing the semantics. Do I understand correctly? There is no formal semantics for AMI?
I think there are some for AMI itself, but not really for the compiler linearization methods.
Okay.
Kathleen, then Gregory.
I guess it's a very naive question, since I was also not fully able to follow the numbers. So is the goal of AMI to make this kind of, how should I say, turning secret dependent branches into running to branches? Is the goal to make this faster? Or is it just a replacement for a simple instruction that selects the result at the end? Because that seems...
The goal is that it would be faster indeed, and that it would also be relatively cheap to implement in hardware. It could still be faster.
So then two questions. Why would it be faster? And can you explain at which column we were supposed to look? Like which one was AMI on the previous slide? Yeah. I didn't understand how to read this graph.
So yeah, it's the linearization method that I've described is the one right here, and so that's around 1.26 on average, and manual AMI linearization is 1.19 on average.
So this means using the hardware but doing the linearization by hand?
Sorry?
Using the hardware?
Yeah, doing the which is slightly more efficient than doing it automatically with the compiler.
Do you have any, like, which one is the baseline in which you would really run one branch, then the other, and then select the results?
Like, that would be the 1.73.
I see. So that's the real improvement, right?
Yeah.
Even if you do it in the compiler, it's still much faster.
Yeah, so just I'm wondering, so these secret annotations on variables, that seems like something that might be useful for other applications as well. have you looked into whether something like that already exists, or whether there are proposals for that, or other papers that have something similar?
I think there are similar work, but I think it's usually more focused on the middle end and the front end, but not on getting this information down in the back end where we need it for a transformation.
Because I remember papers about other like security relevant annotations that people have been proposing to add to C and to make use of in the compiler, like rights that seem not to do anything but are actually there for clearing secrets and so on. And so this seems like another case where you add security relevant annotations to C, which seems like something that would be nice to have in the longer run.
One last question, couple of more. Yeah, we have time actually. Just a side.
Excuse me. So, does your optimization run after things like common computations have been lifted out of the branches that you're interested in doing? Like if you computed something in the top of both branches kind of by accident or something like that, or due to inlining, would that have already been lifted out, or?
I think that would have been done before.
Okay.
Last one. Yeah.
Thank you for the talk. I have a quick question. Is there any uncompatible programs with your linearization approach?
Yes, we haven't really been able to test larger real-world programs yet because the compiler parsers aren't very reliable and polished yet.
I see. Thank you.
Speaker. Let's thanks again then. I also should have mentioned that since we don't have short talks, we are just taking it easy and letting a bit more time for questions and for talks. So, anyways, if you want to do a last-minute short talk, you're more than welcome. And
am I good? All right.
So, Gregory is telling us more about modularizing CPU semantics. So, go ahead, please.
Thank you. All right, so you guys all probably saw Peter's talk this morning about the grand vision of verifying a hypervisor. My grand vision is similar in many respects. So virtualization is this technology that we use to run multiple machines on the same core or on the same computer, in the same way that we run multiple processes on the same operating system. And we can provide a lot of things basically in the exact same way that the exact same sort of features that operating systems provide to processes. Obviously, to provide these additional features, you have highly privileged code that has a great amount of visibility into both your process and adjacent processes, or in this case. And this came out, I think, 2 days ago. These things are vulnerable, and it's a big deal because these things underlie a lot of infrastructure that you use every day. All right, so our goal is to prove this little stack correct. It's not really little, but in the picture, it's not too imposing. And the property we want to prove is let's see. No, that doesn't work. OK, the property we want to prove is a refinement specification. So we want to be able to show that if we run 3 guests on top of our implementation down here, that our implementation will act in only ways that those three guests could have acted if they were run in parallel, connected by these little green network things. All right, and for the purpose of this talk, I'm just going to talk about one of these VMMs. That'll be the middle one, but they're all the same, so it doesn't matter. All right, so the outline of this talk is I'm going to tell you a little bit about what the computer looks like from the hardware point of view in a less scary way than Peter did. And it's going to, so we'll talk a little bit about that. Then we'll focus on the CPU, which is exactly what Peter focused on, because it's probably the most interesting piece, but by no means the only complicated piece. We'll talk about how we decompose the semantics, which will align with great deal with what Peter told you this morning. And then we'll tell you a little bit about how we're aiming to use this decomposition in our overall proof. All right, so if you look at computers from the system level and not from the program level, you'll see all these additional things. We're used to thinking about the CPU itself down here, but there's also things like interrupt controllers and devices. Now in the specification, you might have 3 CPUs and 3 devices, but in the implementation, you'll have 3 CPUs, but some of your devices and things like that might be software virtualized. And so these things that are marked as blue are things that are actually implemented in software and then exposed to the higher level piece as if they were virtual hardware. And as I mentioned, we're just going to talk about this one little box, or this one little refinement over here. All right. So Peter gave a great overview of this. So some of my slides are a little bit redundant, but I'll go through them anyway. So down here, the specification we want to do is we want to connect the specification down here. This is the implementation. So this is going to be ARM running with full virtualization extensions. So an ARM VA, ARM 8 A class processor. And up there, we were going to have ARM kind of without virtualization extensions. So we're not going to support a feature called nested virtualization, which would allow you to run a hypervisor inside of our hypervisor. It's just not necessary for our use cases. And the way we describe this, so that I can fill these boxes with more than just English text, is a combination of 2 things: the instruction semantics, which Peter showed you quite a bit about, and the concurrency semantics, which is kind of how these things get interleaved. And for the purpose of this talk, I'll say that that's ASL and this concurrency semantics down here, kind of linked together by this this guy runs this guy sort of thing. And we can do the same thing at the top, but we're just going to specialize that ASL semantics to not have EL2 logic in it. So we'll just be removing some of it. It'll be a smaller semantics than this, but not that much smaller. All right. And so the normal way we might do this is we might implement a VMM using some software and some hardware. But the problem with this is that this exact implementation isn't great from our point of view, because we want a little bit more functionality in our user space than what PKVM is aiming for. So instead, we break this full refinement into 2 pieces. One is this thing down here, which is a microkernel called Nova. It's like an operating system or a hardware abstraction layer, and it provides the ability to run user space programs as well as hardware virtual CPUs. And then a C++ program, this VMM up here, which will run in user space and provide all those extra things like the software emulated devices and things like that. Now, the semantics of these 2 blue boxes is very similar to the semantics down here in ASL. But there's differences. So all of the unprivileged logic is going to be very similar, but all the privileged logic will be different. And what our goal is to do is to factor those semantics so that we can use one thing for all the common pieces and then just tweak the other box. So basically, we're going to introduce an abstraction layer that allows us to run the same program under different interpretations to fill in different pieces of these boxes. Right, so this is how it works. This thing over here is the unprivileged code. That's what you get from ARM, with everything kind of linked together. And what we're going to do is we're going to draw this line here, and we're going to pull some of the code out into this box down here, which is what we're going to call the privileged code, so that all of these blue boxes are exactly the same. And we'll be able to change these boxes, whether we're running guest CPUs, guest code, host code, or on the physical machine. And the nice thing about this setup is that once I've done this decomposition, the top two layers of this box, SASL plus EL1, running on top of the concurrency semantics, in the specification is exactly the same as it is in the implementation. So the idea is that this will allow us to factor the proof when we're running in hardware virtualized mode to be relatively easy by construction. And the key thing to think about here is the gap between what the actual specification is, the red box, what's written in the ARM manual, and the blue box, which says our decomposition of it. So that's the focus of this talk. That's what I mean by decomposing CPU semantics. All right, so I've got a few little examples. Some of these are more realistic than others, but this is some of what Peter was talking about this morning, so a little bit more code, maybe a little scarier. This is an instruction in ARM that reads TTBR0EL1, which is the page table root at execution level 1, so operating system mode. And this is what you'd get if you, I think this was copied out of the one of those many web pages that tells you the semantics of what these instructions do. So what we have to do in order to decompose the semantics is we have to identify what the privileged state is. Now we're at EL1 here, so we should have access to all the EL1 registers. But you'll notice that to compute the answer even when you're at EL1, you need to look at some EL2 state, which is hypervisor state. And we don't want to expose that state to the unprivileged logic, because then we won't be able to intersect it. We won't be able to know that these checks are being executed correctly and things like that. So we decompose it, and we end up with this relatively simple unprivileged program here. And then this slightly more interesting handler, which does all the checking of EL2 and just returns the appropriate value of TTBR0EL1. And so using kind of regular old functional programming language equational theory, you could see that if you were to link this program with this program and then do all the normal jump threading and whatnot, you would end up with something akin to this program over here with the gray pieces already highlighted out. All right. So that tells you a little bit about what it looks like when you have some interesting control flow. The more interesting thing, and that happens all the time, is actually memory accesses. And this is the memory instruction, LDUR reads, does a read of memory. And I think Peter actually showed this mem relation on his slide, or this mem function on his slide, and told you that it does things like splitting accesses and doing address translation and all that. And we do, so we focus on that piece. The rest of it is completely unprivileged. And, excuse me, we can rewrite this bottom piece. We can meet essentially the same interface, but basically all of this stuff occurs in the unprivileged mode. So you ask to translate the address, then you ask to read the address. And the nice thing is that this address here, the unprivileged logic is only ever going to see virtual addresses. It's not going to see the actual physical address. So we'll be hiding that from the unprivileged logic. And we'll also be guaranteeing that every time you do a memory read, you'll be accessing the virtual address and we'll be able to show that the translation is done correctly anatomically. All right, so this memory interface looks like translate an address, which gives you this handle and some information about the permissions, so the permissions can be checked. But then you also have read and write, and the permissions and the address translation is validated again using this handle inside read and write, and that ensures things like TLBI flushes and whatnot are like that the unprivileged semantics is not using very old translations to continue to read after those translations were invalidated. All right. I don't know how I'm doing at time, but okay. There's not even a timer for me. This is wonderful. Okay. All right, so I told you a little bit how we decompose these semantics, and we're basically at this. So I told you that this simulation relation over here for when we're running with hardware virtualization. So we're not running our C++ program. We're actually running a core, and ARM is doing the virtualization for us. Is relatively easy. I'm going to give you an intuition for what this simulation looks like and what we end up having to prove in our overall proof. So you imagine you're just starting the computer. You have a register file, but you haven't started executing any instructions yet. Effectively, we're going to say that the implementation and the specification have the same pipeline state. Okay, the registers are the same, and there's no speculation or anything like that going on right now. So the pipelines are in exactly the same state. So those will be in our relation arm. As we start executing, we're going to assume that ARM got virtualization correct. And so if we take a step in the unprivileged logic, the unprivileged semantic says, move register R1 to R2 or something like that, then that will go, it'll start advancing the pipeline state. Maybe we were fetching new instructions or whatnot. But those will be similar as long as we're staying within the CPU itself. Okay? So these aren't things that hit memory or anything like that. Now, we'll run along, and at some point, we might realize that in the implementation, there's a fault. Because, for example, second stage address translation said you're not allowed to read this page that you're trying to read. But in the specification, there's no fault because we're emulating a regular machine that has no second stage translation. So in this case, the relation is going to relate the implementation, which is basically one step ahead, one faulting step ahead of the specification. And we'll be able to quantify exactly why that fault occurred using this red box or this red circle. When we continue to run, we might get to a point where that red circle is the next thing to do. We need to take this exception. And in that case, our Nova kernel, the microkernel, is going to take that exception. It's going to transfer control down into Nova, and then transfer it back up to our VMM. And now our VMM has two choices. One thing it could do is it could roll back the semantics, so despeculate that, maybe fix up permissions in the table. Maybe you're doing a lazy paging or something like that. And then just start again and say, try again. I think I fixed the problem for you. The other choice it could do is it could actually try to emulate the instruction, which is necessary when you're talking to software virtualized devices, for example. And we could try to finish it by using information that's expressed in this fault called decode assist registers. Ultimately, either one of those that we do, the obligation we need to do is we need to get back into a state related by R. And the only way you can enter virtualization mode is if you're in an architecturally stable state. So both of those transitions, either despeculating or finishing the instruction, will get us into appropriate states there. So that's basically the end of the talk. I walked you through our idea for decomposing CPU semantics, which aligns very well with what Peter and company are working on, and how we're ultimately trying to fit this semantics into the overall proof of this bare metal property, the specification for our virtualization stack. So that's it. I'll take questions now.
So questions? Dominique?
Just to make sure I understand correctly, so what you did is you took the original ASL spec and you manually rewrote it by separating out these two pieces, and then you established, then you worked with the rewritten spec and proved a simulation between running on a isolated machine and running in a VMM.
That is effectively correct. Well, I'll give you, like, what I've presented here is our proposal for how we aim to do this. We have done this with several instructions and kind of given an argument for how that fits into the proof. So the VMM is quite large, and we've verified quite a bit of the C++ code. And we have this question, what is the specification for now start running in the hardware? So what we've been doing with this is kind of doing on paper that decomposition for several instructions, kind of identifying that interface between the hardware and the software, and then doing some proofs about when this fault is taken or when memory is executed, how does that integrate with the software iris invariants and whatnot that we have.
Right, and so this rewrite of the ASL spec into a different form, have you proven anything about that rewrite, or is that not part of the goal? Is it?
That is part of the goal. The degree at which we've done it is kind of what's expressed on these slides. So we've done this for various instructions and argued kind of informally on paper, but not in a mechanized sort of way yet.
Interesting. Thank you.
Sure.
Other questions? No, we have plenty of time actually.
Okay.
So, yeah, I just wanted to reiterate on, I think this one.
Mhm.
So, you come up with this splitting, let's say.
Mhm.
How? I mean, manually, or, because if you want to do that for all the ARM instructions, then.
Yeah. So ARM is let's say, slightly more sane architecture than other architectures. And Peter mentioned that there are an enormous amount of, the semantics is very large, but relatively little of it mentions privileged state. So there's lots of instructions that are completely unprivileged, like add and whatnot. We believe we don't have to do anything to those. But there's still things like memory accesses and maybe 100 MSR registers. To do this kind of in an automated way, you'd probably want to do something like taint analysis. So you could look at this original program, identify any paths that are influenced by state that's outside of the privileged component. So this would be EL2, for example. And that would be able to flag for you the places where you need to abstract. Whether you could do that abstraction completely automatically, maybe you could in some instances. Like this one I could imagine maybe doing. Other ones maybe a little bit less. Like the memory one is quite subtle. Yep.
Yeah, I was also thinking about, because if you think about, I don't know actually, but my guess is that you may have non-trivial, it's not easy to identify, I guess, I don't know, but it seems not so easy to identify exactly which has to do with, control flows that has to do with privileged state and whatnot, right?
Yeah, I think I'll speculate it might not be terribly difficult, but I'm not sure. We know which variables and whatnot, like which pieces of state are privileged, so it's a matter of doing like a taint analysis.
So
I think.
That's the ground truth. I was thinking about maybe the manual says, oh, this is not privileged, but then it touches something which is.
We can determine what's privileged very, very clearly by looking at what state is controlled by EL2 and not visible to EL1. So we have a very mathematically rigorous way to determine that.
Okay, yeah, that's fine.
So something I'm not seeing. So how do you connect your code is mostly written in C or C++, I think. So how do you connect the ASL state or the ASL representation of architectural state to the C++ state? Or to the way you access this ASL state from C++? I guess you have some way of doing that.
Yeah, so let me see if I can. All right, so here, what happens when you take a fault is in the architecture you transfer control to the hypervisor, and that writes state into some memory blocks. Those memory blocks get copied up into software selectively by Nova. And then software handles what's going on, and then software will write data back, and Nova will copy that information back to this state as well. Does that answer your question, or not quite?
No, you were talking about, I think, the implementation of Nova in C++, right? And that's the part you're verifying in C++.
Both Nova and the VMM are both implemented in C++. In this talk, I just talked about the VMM, the verification of the VMM. And in that case, we have a specification for what it means when, if you stay for the next talk, not in the next session, you'll hear more about this, but what exactly is the specification for what happens when this thread faults due to a memory access fault or a privileged state access fault or something like that. And that gives us a specification for what we'll know basically at the beginning of this function and what we'll need to establish at the end of this function. So then this becomes a standard C++, you don't have to worry too much about hardware, except for the fact that it's running concurrently with you.
Right. And do you have some way of connecting? So you have specs then? So do you have some way of like, you use these specs on the C++ verification side? Do you have some way to connect them to the ASL view on things, or?
Yeah, that's done because the Nova specification is expressed in separation logic. So the state, the register state of this thread running, this hardware thread running, is a separation logic assertion. We can say its state is currently this, and that state includes all of this, things like speculation. You might be speculating this. You might have this register has this value at the first green box and this value at this other green box and that. But the nice thing is that we're not proving programs that run in the guest. We're focused on running and proving the VMM, so we just treat it kind of as a black box. That's the nice thing about the simulation. Because that simulation is lockstep, we don't really care how it's constructed. We just care about how it interacts with the outside world.
Okay, thank you.
No problem.
So I guess time's up.
Peter has a question
very
too.
Fast one, yeah.
Both, I think.
Yeah.
So that might be a problem. So we talked a lot this week, and that was great. And I think I have some clue what you're doing that I didn't before. And it may be that the answer to this question is not very fast, but somewhere there has to be a proof that your sort of local reasoning of the C++ is soundly gluable onto all of this, right? So somewhere there has to be some proof that if you're using the operational model, that all that excessive amount of potential interleaving can soundly go away. And I think I still don't understand where you imagine that piece of the proof goes.
Time constraints, but what I can say is that we're assuming we get to use C++ reasoning when we're reasoning about our C++ code. And the state that the C++ touches and the state that the guest can touch is very independent, with the exception of very specific points, which are, I believe, done with special operations. And those special operations get interesting specifications, but most of the C++ code just has regular specifications, if that makes sense. If not, we might need to take it offline.
Yeah, my question is sort of, how do you know that that's a sound way to argue? But we should talk about that some more later.
Absolutely.
Okay, so thanks Gregory again.
Thank you.
And a bit lower and on your right.
Can everyone hear me? No? No. Okay. Higher? How about that? Yes?
Does it work? Okay.
Try it without this. Yes?
Okay, perfect. So our last speaker for this session is Andrew, and he's gonna talk to us about ABIs and how binaries talk together, I guess.
Yeah. Hi, everyone. My name is Andrew. I'm going to talk to you a little bit about application binary interfaces, ABIs. Also, if it's okay with the organizers, I'm fine to take questions throughout if that works for you all. Okay, so this word ABI is kind of a scary one sometimes. I came across this article just recently by someone who works on ABIs for a living, and the words they use are 3-letter demon and a contract was forged in blood, which is like a little dramatic. And there's this mystique around ABIs. And I think really fundamentally the reason is that we don't have a good real definition for what an ABI is or what an ABI should be. If you try to find out, usually you get answers like what is in an ABI, like what an ABI has, but not necessarily what it is. Like it has to cover things like data layouts and calling conventions. We know those things. Name mangling is another one that comes up. But if you read ABI docs, they're like allusions to other things that are a little bit more semantic, like safety invariance and ownership. But those don't ever really come up in the definition of what an ABI is. But I think this question is becoming more and more pressing because there are all these new systems languages who are really starting to care very deeply about what an ABI is and what an ABI should be. And I think everyone in this room, at least implicitly, cares about what an ABI is. And some of the problems that we love in this community really can be phrased, I think, as ABI problems. So let me give you a few examples. We've got 2 arbitrary blue-lang components here. They're interacting over some interface, which I'm using. They're sort of like puzzle pieces. This interface, for now, you can think of it as like a type, let's say. And we have some nice type system. I know it's OK to link them together there. But a problem that we love in this community is separate compilation, which is that it's all well and fine if our type system says that they're compatible. But after we compile, are their implementations still actually compatible? And that might not even be with the same compiler, right? We could be compiling with completely different compilers like GCC or Clang, or even different compiler versions. And if we want to make sure that we're in sort of a nice language ecosystem where people have the flexibility to compile differently, we need to ask the question about what is sort of the standard that compiled components can expect to follow to make sure that the linking works out still at the target level. And with this in mind, it doesn't even need to be the same language on both sides, right? We think a lot about interop in our group. And mostly in recent years, we've been thinking about interop at sort of this level, the source level, right? So I have my 2 languages here, the blue lang and the green lang, and I want to put them together. And there have been all sorts of cool ideas about what sort of source level mechanisms we can introduce to interface these 2 languages. So like multi-language boundaries is an operational approach Matthews Findler introduced back in 2007. More recently, my colleague Daniel presented this idea of linking types, which is a type-level approach to bringing types from another language into your own language. But I mean, more generally, like just about every language out there has a CFFI. And if you've ever had the pleasure of working with a CFFI, you know that's not necessarily the best mechanism, but like it is a mechanism. We all do it. It's essential. And there's this same question, really, of after we use any of these mechanisms, whether they're sophisticated or a little bit more rudimentary, we can ask the question, how are we laying things out? Is it actually safe for them to interact after we compile? And there's one more application that I think is really important. It's a slightly different setup than the previous 2, but it's really important, especially for all those systems languages that I mentioned before, which is shared libraries. Okay, so there are some libraries on your computer that just about every other application uses. And it's really important that we're able to update those libraries without forcing everyone in the world to recompile, right? Maybe that's a security patch. Okay, but after we do that, there's a really serious question of whether all those old clients that we didn't want to recompile can actually still run with the new version of your library. If you've ever found yourself in DLL hell, I think everyone has at least once. This is like an instance of that problem. And really, this can be phrased as a question of whether you broke ABI and what kind of updates you're allowed to make without forcing all your clients to change their interface. That can be phrased as an ABI question.
And so as I mentioned before, there's a sort of growing dissatisfaction with the status quo in certain language communities, especially communities that have slogans like rewrite it in Rust. If you want to be able to sort of move forward, we have to ask ourselves whether, like, we're in 2024. If you want an FFI between any two languages, like, chances are you're going through C. Like, is that the best that we can do these days? And actually, if you dig around in the Rust internals, there are a lot of times where Rust's compiler is laying things out like C would lay it out, just because it's convenient and stable, and everyone knows it's not going to change. And that's kind of funny, I think. And there's, I put it up on the slide before, there's a brand new RFC for Rust to tackle some of these questions about where they should go with an ABI, whether that's even a good idea. But this is sort of uncharted territory. We don't have a lot of data points. We pretty much have C's ABI. Some compilers have internal ABIs, but they're not stable. And then we have Swift's ABI, which is pretty bold, and I'll mention some of the ways that that's the case later on. But I think as a compiler community, we have a unique opportunity here to sort of influence the way that things play out. And the question that we're interested in is, can we provide some sort of semantic foundation that would lay the groundwork for making some of these big decisions? And I think in order to do that, we have to actually answer that question from earlier, like what an ABI is and not just what an ABI has. And I think really the question from my perspective is a very simple one. If I have some source interface, which is specified maybe in like a header file or something, again, you can think about it as like a type for now. What target programs does it describe? If I'm linking against this interface, right, which target programs, which components should I expect to be able to link with? Yes?
Target means an assembly. Target means an assembly language or one specific target? Or?
It really, technically, it means a platform. But we'll see in the setup in a moment. What at least the Rust proposal has been so far is that instead of starting all the way from scratch, we can build on top of another ABI, which is C's. So because the C's ABI is defined on every platform already, we can reuse some of their basic ABI mechanisms, like which things will go in registers and which things will go on the stack. We can reuse that. Okay, but there are some bits we want to add on top. So for now, you can think of it as whatever your lowest common denominator is. That may or may not be assembly, depending on which way you want to go.
Right. So maybe just as a comment or a question, I don't know. So, but the way I understand is the fact that every language uses C as an FFI is largely because that's a common denominator, and because you don't want to specify for every target independently.
Yes, and in fact, we're going to see in the concrete example, it's going to be C that we're going to build on. Yeah, because it's very convenient. I should say, we'll talk about it at the end. We have some other ideas for alternatives. I guess I could give a spoiler. WebAssembly would be another good choice, we think. Great question. Yeah. OK. So I think this is like the intuitive role that an ABI should play. It's sort of an expansive definition, I think. But when we're talking at this level of the semantics, I think it's a useful one. And to make this ever so slightly more formal, again, for us, an interface, at least right now, will be a type, right? And really, we're just asking the question, which target programs behave like that type? Okay? And if you happen to catch Amal's keynote last year at PriSC, this may look familiar to you. She talked about realizability models and semantic typing. If you have not seen that before, I'm going to cover it again, so don't worry. But this is sort of the core idea. For now, you can just think of this as some set with a very, very fancy predicate on target programs. Okay? And then the question of ABI compliance, right? Like, am I actually following this standard linking protocol? Is, there's a lot loaded in that containment, but like that's really the ultimate question: is do I satisfy the model? Okay. Now, semantic typing realizability models, that's something that we've been working with for the past couple of years. But we've been using it as a proof object. It was like a means to an end. And what I just gave you was a definition. Okay. So there's this really, I think, interesting question which doesn't really have like a straightforward answer. It's a qualitative question. Is this a good spec? Like, is this a good idea? Is this the right way to talk about ABIs? And I think there are sort of two questions we need to answer in order to evaluate that. One is about the spec itself, right? So ABIs, they have to really get into the weeds, the nitty-gritty. Can you actually get low enough of a level with this kind of specification? I think we've seen a lot of promising efforts over the years to indicate that that is the case, but it still is an important question. Like, will the ABI committees buy into this idea? Will they accept this as a kind of definition that they can work with and write compilers against? And then the other one is the way that it's going to be used. Oh, yeah.
Any question that begins, will the committees accept, has the answer no.
Yes.
They have a fine bunch of APIs. They've been stable for I don't know how many decades. They're great.
Yes. No, I think that's a good point, is that, you know, there's a precedent, and the reason that, as someone mentioned it before, the reason that everyone uses C's ABI is because it's there and it hasn't changed ever, and it probably won't change ever. And there's a lot of benefit in that. Had there not been any of these RFCs, had Swift not published an ABI stability manifesto, then I would not be interested in this question. It would just be C for the end of time. But I think there is sort of a growing demand to do something a little bit richer and move forward. Okay, and yeah, the second one is just, so there was the formalism itself, and then on the second aspect of that is we should be able to prove all of the examples that we saw before and potentially much more. Yes?
Yeah, just to understand, I mean, couldn't the C ABI also be specified in this way?
Absolutely.
Okay, so then it's not about changing it, it's about whether this is a good way to specify it.
Absolutely, it could, yes. Okay. So to make things a little bit more concrete, we're going to look at some examples covering those 2 points, both the formalization and the applications. In this example, we'll take a sort of functional language that you'll all be familiar with, and the target, like we just mentioned a few minutes ago, will be something C-ish for now. You can keep that in mind. Even though there's no references in the source, the implementation is going to box all the values, at least for the purpose of this talk, just to sketch out some of these ideas. And the way that we're actually going to specify the ABI itself, specify this model, I said the predicate would be pretty rich. It'll actually be given as a separation logic specification. Okay. So if you have not seen semantic typing before, the key idea is that we want to characterize which dynamic terms behave like a certain type. Okay? So we're going to keep our typing judgment in mind. Right? The only twist that realizability adds is that the program that we're using, the program that's running that's supposed to behave like that type, is not actually drawn from the same language as the type itself. Okay? So in this case, the question that we're asking is, when does a target program behave like a particular type? Okay? And intuitively, if using like a Hoare triple notation, right? We just want to know if we have some pre-state that sort of acts like a gamma, right? And we run that target program, then we should get back a value that behaves like a t. Okay, that's like the core idea. And like I said, at least for this example that I'm going to show you, we're going to box everything. So we're just going to take the result. The result should be boxed. It should behave like a reference to a t. Right? It should be some location that acts like a reference of a t, and everything in our context, those should also be references. So if you're like, what is this R thing? I'm punting the definition. It's going to be on the next slide. But for now, intuitively, it says if you give me a bunch of references that satisfy my context, then I should run to a value that behaves like a t. Okay? So what is this reference thing? Well, one of the things we have to do is we have to specify the layout. So all of our references are going to be laid out like this. We have the counter in the first position, and then we have some object adjacent to it. Okay. And we're going to do this for all of our types. So the references have a uniform representation, okay? But all of our different types will have a different object representation. For example, integers, right, will have pretty much the natural representation, right? It's just going to be some integer sitting there, okay? And we're going to do this for each of our types. I should say, if it bothers you that we're boxing integers, you could very easily modify this so that R was not necessarily a uniform representation where we're reference counting. You could use something like pointer tagging to get unboxed data, and that's something that we've been experimenting with as well. Okay, so this is one bit, is like the data layout itself, right? But the way that these references behave, we want to capture richer properties than just layout. The way that these properties behave is a key part, I think, of moving toward a richer specification. So really, each reference in this logic will come with sort of a lower bound on the count. Okay? So if I have one reference, then I know the count's at least 1. And likewise, if I have 2 or 3 references, right, I learn that the lower bound on the count is higher and higher and higher. Right? If you like rules, then the rule would look something like this, right? If I have a reference, I have the permission to increment that reference. Okay? And I do know that the count is greater than 1 by virtue of having it in the first place. Yeah. Oh, 5 minutes, okay, yeah. And I can go in the other direction as well, right? So if I start with 3 references, I can go down and down and down, but of course, each time I have to be a little careful, right? Because when I have a reference, I don't really know, it's just a lower bound. There could be some other reference out there that I can't see. This is like your frame condition, okay? And then the count would be strictly greater than 1, and when I drop it, well, I don't know, the count's greater than 0, I don't have any of those references, and I don't keep any reference to this object whatsoever. So I get back nothing. I have no obligations, and I also have no permissions regarding that pointer, okay? The other case is when it's exactly 1. Sorry, I skipped ahead. The other case is when it's exactly 1. This really is the last one that's remaining, and in this case, right, once I decrement, I've gone all the way to 0. And importantly, I get back ownership of the underlying object. So a way that you can think of a reference is it's sort of a permission to increment and read and all of those things. But it's also an obligation to decrement. This is going to come with resources that need to be collected, right? So this might have references of its own, and those will need to be dropped for garbage collection reasons, right? So you get back permission to call the destructors sitting in O. And this shape is pretty much like the reference shape that we started with. In fact, if you set it up properly, right, and you initialize the count to 1, well, that's how you can introduce references in the first place, right? These 2 views, this is just a view shift on the same data. So we don't just care about the layout. We're specifying the whole protocol, which includes how you should be interacting with them, how you should manage the logical state in addition to the physical state. Okay. And this is going to carry all the way throughout. So that was a bit about the reference protocol. But even when we go to layout, right, if we're thinking about how we're just going to lay out pairs for now, right, if your ABI was just specifying the physical resources, you'd probably start your specification like this. Okay, we have a uniform representation, so it's just going to be 2 cells with 2 pointers in them. And you'd kind of stop there, right? That's the data. But it's more than that. The data comes with these resources, and those are essential to the protocol as well, right? These might have their own counts. Then we're going to have their own resources that you need to manage as well. And in this case, I guess the layout is very maybe clear because we have a uniform representation, and it's just a tuple. Laying them out adjacent to each other is maybe the most natural option. But if you have records and variants, you really have to think carefully about how you're going to order the fields and things like that, because whether you're sensitive to the ordering of the fields, whether you're able to add new fields, these are all things that are going to come up in this very definition. Okay. The other thing that an ABI is supposed to do, in addition to specifying layout, is calling conventions. So fundamentally, as a piece of data, a function is just going to be a function pointer. But again, we're going to specify more than just the representation. We're going to specify the calling convention here, right? So here this says it's a pointer to some function pointer, but we want to know what happens when we call that function, given something that follows the protocol. So in this case, the calling convention stipulates that when we call this function with a reference of input type, it's going to consume that reference and give you back a reference of output type, right? But importantly, it's consuming it, it's not giving it back. There's another totally viable option that's used sometimes in reference counting schemes, right? Which is that you have to give back the reference. And if this is sort of analogous to like caller save versus callee save. In this case, the former is like caller retain, or caller increment if you like, right? Whereas here, right, the callee is going to have to increment if they're going to do anything interesting with it. And this is just with sort of bare functions. If you had closures, right, closures would even need to consider more. They would need to account for how the environment is passed in the closing convention, the calling convention, and there's a lot of subtlety that you can express just at this level. Okay. So that was just a taste of some of the aspects of the formalization or a potential formalization. When it comes to applications, when it comes to using the formalization itself, this was one setup that we were interested in the beginning, right? Whether we can link code from different compilers. Well, if we show that they are both compliant, which is to say they only produce compliant components, right? Then we sort of get in the way we usually do, compositionality from the semantic typing, right? We can put them together because their semantic types are compatible, right? And just as I mentioned earlier, this isn't limited to code from the same compiler, right? It can be code from, code from the same compilers for the same language. It could be compilers for completely different languages, although most likely you'll want to show something additional here, right? About the relationship between the FFI code and the code sitting in that other language, right? Showing that actually there's some relationship between the types on the other side and the types in that green language. I would love to talk more about that if folks want. And then in this last one, the library compatibility. Really, you can think of library compatibility as sort of like a semantic subset. Right, so before it satisfied some ABI, and it needs to continue to satisfy the same ABI, which means it's compliant at the same type that it was before. And if you're thinking, well, when can I, like, what kind of changes here are interesting? What kind of changes are allowed? Swift has done some very interesting, made some very interesting decisions in its ABI. And it sort of allows a lot of flexibility in the kinds of changes you're allowed to make across libraries by default. So for example, like adding fields to a struct, adding cases to an enum. Things that like we get from nice type systems, but the ABI hasn't really kept pace. And people who are writing shared libraries in C are already doing this kind of thing. They're just doing it by hand. If you go and you look at the way some of the sort of long-lasting shared libraries are written, they'll be written with all these extra fields at the end, with null pointers most of the time. And if they ever want to add the fields, right, they'll add another layer of abstraction on, right? And they're doing this thing by hand. Whereas Swift said we want to give library authors that support by default from the language. So there's a trade-off space there. Obviously, Swift has to resolve some things more dynamically, but it's an interesting space to explore. And with a setup like this, you can actually analyze those kinds of decisions. So we're working on this case study now with a bunch of variations, some of which I alluded to throughout the talk. And I mentioned some of the idiosyncrasies of Swift's ABI that we're trying to look at. They call these resilient type layouts that are sort of accepting of certain changes to the type definitions. And they do some interesting things with polymorphism as well, because they care about code sizes. Monomorphization is not an option for them. So they have to do some interesting things to move representations. And something else we're thinking about, we're working on, is an ABI for Rust. Again, this is an active area of discussion within the Rust dev team. And we're looking at potentially doing this over WASM instead of C, specifically using the component model, which we think is, they're sort of like building blocks, we think, that you could use to construct layers of ABI abstraction, right? So you're right that you don't want to start from scratch every time. And this might provide the right sort of vocabulary for doing that thing and making it easier for languages to specify their own ABI without starting from the bottom. Okay, so that's it for me. This is sort of the pipeline that we're analyzing now. And I'd love to hear your thoughts on this. So I'll be around. Reach out to me if you have questions or you want to talk. Thank you.
So we are ready at questions, but feel free to ask.
So some of your ABI specifications seemed a lot like correctness conditions, like Hoare triples and whatnot.
Yep.
Can you say more about like how you would write those and how you would relate them to like C has a notion of what a pointer is, and that's not the same as the notion of a pointer at the level of assembly. So do you have an idea of how those would be connected?
Yeah, so I think there are sort of two questions in there. So at this level, we're mostly thinking about safety, and so not fully functional correctness, although that's probably something you'd want to show at least for the compiler example. It's not necessarily the ABI's responsibility, though. When it comes to I think you're saying the gap between the memory model of C and the memory model of the underlying architecture. That's a really great question. And I think ultimately, if this seems like a good idea, then it would be nice to also show C's ABI in this way. Of course, that would be per platform. But for now, we're just imagining this as the lowest level that you're going to go between. So like I mentioned before, Rust's team is looking to inherit the interpretation, at least for now, inherit the interpretation of pointers from C, at least at the level of its ABI. Whether that's the right decision, I don't know. But for now, they're just sort of taking it at face value, it seems. Yeah.
Okay, thank you.
One more, yeah.
So it's an interesting idea to use WASM instead of C for as a sort of common denominator. I guess one advantage might be that you have a sort of security spec for WASM, which you generally don't really have for C. So
yes.
Is that part of the goal? Is that, or
I think that's part of the goal. Mostly, I mean, we're really interested in. I mean, one of the applications here is interop, and that's one that we're really interested in. But yeah, for security reasons as well, I think it's a very interesting application. And also, I mean, we'll see where the component model goes, but I really think at least the motivation there, it sounds like they're sort of establishing a vocabulary for building up ABIs that not only can you specify, but you can also type check them, which is a very, none of this was about type checking, but theoretically, if you could type check compliance, that would be, well, that would be amazing. So that might provide some sort of path to that. Right now, if you were to do this, targeting C's ABI, that would just be too hard to type check at this stage. Yeah.
Can I ask another question? So one thing that does strike me as weird is that you don't, your ABI doesn't seem to specify how. It just says what are the possible legal values, not how does one source value correspond to one target value, which.
So that would be something that you'd want to show specifically for compiler compliance, right? You're probably not just interested in the compiler being compliant, but also that it's correct.
If I think about an ABI intuitively, then I think about how is a Boolean represented, not just what are the legal values that represent some Boolean.
So you're saying it should be more of a, how is a particular Boolean represented?
Yeah, I mean, if I think intuitively about an ABI, that's part of it for me.
Okay, that's an interesting idea, yeah.
If I can also add another question. So maybe the bit that I'm missing is how does this, your model of an ABI actually I mean, different languages have different assumptions on, I don't know, how, wait, let me rephrase it. So, okay, here's an example. I'm thinking about, C C code interacting with Rust code. They have different approaches to memory management.
Yes.
And here you're like thinking, okay, we put everything in a box and everything is reference counted, but
yes,
that's not like how people are, people that develop, like C Rust applications work. Like they, on some, if the object is like a Rust object, then is like reference counted. If it's from C side, then if it's coming from C, then it's just a pointer to a buffer. And so what I'm wondering, and I'm thinking, whether you have ideas on how to capture that. Is this more subtle, maybe patterns? How could they how could you make this explicit in your model? How could you guarantee that they work together?
Yeah, that's a great question. So to be clear, the boxing is that's not a fundamental to the approach. That's just for this particular case study. So for Rust, you would not do that. You would do something different, where you'd model sort of their ownership, their notion of ownership, and it wouldn't necessarily be reference counting throughout, right? But this notion of moving between C and Rust, right? That's something that's very tricky, but people are already doing that. All of these things people are already doing, and we just want to give some sort of handle to make some handle on that you can formalize what they're doing, and then hopefully eventually verify that they're doing it correctly, right? So there are these FFI guidelines for interactions between Rust and C, okay? And it's a nice list, but we don't know if it's correct, if it's exhaustive, right? It's a good sort of baseline, but this would potentially let you say, right, that if you follow these guidelines, right, then your migration from one ABI to another is correct or sound. Yes.
Last one.
I mean, true, that. I mean, whether they're correct or not, I think it's not something that current ABIs really talk about. What ABIs nowadays are about is just, okay, you pass a pointer, you pass an integer, and that's about it. And then how you treat them, so the rest of the application has to do in, and maybe this is why this is challenging, has to know what's on the other side.
Yes.
To use them correctly.
Yes.
So yeah, I guess maybe. So it's maybe, ideally, I guess, an ABI should, an ABI spec should include this type of information, maybe.
That way you know at least what the endpoints are, right? So
Yeah.
you know how you have to move between them. That's the goal, yeah.
Cool, great.
Thank you.
Okay, maybe. Yeah. I mean, it's coffee time almost, but
yeah, sorry, just a quick comment. So one
Yes.
thing that struck me as missing is a story for a language like Haskell, where you can, when you use an FFI in Haskell, you can say this C function is actually a pure function, so I'm gonna not run it in the IO monad, or I am gonna model it in the IO monad, or.
Yes, if you go here and you look at linking types, right? That's what I was saying before. There are different source level mechanisms for interacting across languages that are really, really important. Of course, in that scenario, you don't actually know. You could mark something as IO and it might not really be IO. So that's still an issue. It's still a risk. But the types that you assign to foreign code, yeah, that's a very interesting issue, and it is something we've thought about, but not explicitly as part of the ABI, but as part of a compiler extension that lets you write the same way that you do foreign import in Haskell. Yeah, I would say that's more of a compiler issue than an ABI issue in its own right, but you can use the ABI to make sure that the type you're ascribing is coherent. Right, once you've imported, the fact that it's extern doesn't stick with the type. I wouldn't say it's part of the type. Okay, yeah. I'd love to talk more about it, yeah.
So let's thank Andrew again, and coffee.
Great. Welcome to the last session of PriSC and the last session of POPL'. So I have been asked to try and stick to the schedule because it's sort of the last session of POPL'. So I will quickly try to give the floor to Ethan. Ethan will tell us about secure compilation in a context we haven't heard yet today, which is cryptography.
Great. Thank you, Dominique. So yes, as he said, this talk is really about connecting two domains. And given where we are right now, it should be pretty unsurprising that one of those domains is programming languages. And given that Marco is one of the chairs of this workshop, it should be also pretty unsurprising that specifically I'm going to be talking about robust compilation on the programming languages side. And the second domain, as Dominique mentioned, is cryptography. And in particular, I'm going to talk about universally composable security, or UC security. And so we want to connect robust compilation and UC security. Now, I don't expect everyone in here to know what UC security even is. So as a quick primer, this was originally introduced by Ron Canetti a little over 20 years ago. And it's a framework for defining and proving the correctness and security of cryptographic protocols in a way that ensures that they compose really nicely. So at a very high level, you take an actual protocol, which we're going to call Pi, and it has a bunch of different machines, and they're all talking to each other. And we're going to define the correctness and the security of Pi with a so-called ideal protocol. And an ideal protocol, instead of having all the machines talking directly to each other, it has all the machines talking to a sort of magical trusted intermediary that's known as the ideal functionality. And the ideal functionality defines what it means for the protocol to be correct and secure. And at a high level, the security proof would work as follows. We would say that for every attacker, right, maybe we replace one of the machines has been compromised by an attacker. And so for every possible attacker who can compromise that machine, we need to be able to find some simulator such that both of the sides of this diagram kind of look the same as each other. And they need to sort of behave the same way. And that notion of behavior is that we're going to take some environment and we're going to put the same environment on both sides. And we're going to say from the environment's perspective, this has to look the same. And we quantify over all possible environments. So that's what universal composability says. It says if no environment can tell the difference between these, then the protocol is correct and secure. Well, as sort of a recap, what does robust compilation look like? Well, there's a lot of different kinds of robust compilation. We've heard about multiple different kinds already today. And specifically, I'm concerned with robust hyperproperty preserving compilation, or RHC. This is from the Journey Beyond Full Abstraction work from CSF 2019. And in this context, we have a compiler, which in this case we'll say takes these blue square programs to these orange circular programs. And we say, well, for any source language program and any target language context, we have to be able to find some source language context such that the behaviors of these are exactly the same as each other. But we can, that's sort of the original formulation. We can take that formulation and we can look at it slightly differently. We can, in particular, we can split the context into two pieces. Right? We can sort of think of the context as an adversary, and then there's some environment, and all the environment is doing is it's supplying inputs to the whole system, and then it's just going to watch an external view of what's going on. The adversary is going to do all of the actual work that the context was doing. And we say, well, we can sort of do the same thing on the other side, right? We can say, well, there exists a simulator that does the same thing. In the context, it's just providing external inputs and it's when watching what's happening, nothing else. So it's going to be the same environment on both sides. And so instead of behaving the same, we can say, well, these kind of look the same to that environment. Boy, this looks familiar. This picture is kind of the same picture as the UC picture we had up earlier, right? I can just put these next to each other. And these have exactly the same structure. And so we'd like to relate these, but if we want to relate them in a really technical sense, we need to have definitions for things, and more formal definitions than just sort of this wishy-washy hand-wavy stuff I've been saying. And the first one I want to talk about is this notion of looking the same. I have not told you what that means. And there's a lot of different ways to define looking the same. The simplest one is just equality. You just say these two things have to be exactly equal. And if we do that, we actually get very well understood notions on both sides. We get something that's called perfect UC security. These behave exactly the same. And we get standard robust hyperproperty preservation on the robust compilation side. And thanks to some work by Marco, as well as my co-author on this, Robert Kuhneman and Riyad Wabi, we actually know that these do fundamentally deeply represent the same thing. That's not new to me or to the paper I'm talking about here. But unfortunately, on the UC side, that equality symbol is kind of a problem. Perfect UC security isn't very useful in many contexts because real cryptography isn't perfectly secure. Real cryptography is only secure against computationally bounded adversaries. It makes hardness assumptions on the difficulty of computing problems that are often trivially decidable. They just require perhaps exponential time. So let's fix this. And to fix this, let's look at what people actually use. And on the UC side, we have a well-understood notion of what people actually use, which is computational UC. And this is to handle the fact that, as I said, cryptography needs computational bounds. So we can take the same picture we had before. We can just start kind of tossing computational bounds on it, right? We can say, well, the attacker has to run in time polynomial in the length of the input. And the simulator also has to run in time polynomial in the length of the input. We're not going to care about attackers that take longer than that, and we're going to require that our simulators be that fast. We can say, well, the environment's only allowed to use polynomially much computation to try to tell these things apart. And the last thing we can do is we can put a weaker notion of looking the same onto this that's referred to as computational indistinguishability. And this just says that they don't have to be exactly the same, but to the perspective of this computationally bounded environment, the difference between them, its ability to tell which side it's in, has to shrink really, really fast as the length of the input grows. Really fast here usually means exponentially fast. So this is what actual computational UC looks like. This is what people in the cryptography world use when they're talking about UC security. And so if we want a notion of robust compilation that corresponds to this in any meaningful way, we need a notion of computationally robust compilation. We need to sort of get these computational bounds into the robust compilation world. So to do that, where's the problem, right? Well, robust compilation talks about all contexts and demands that the behavior be exactly the same. So to fix this, we're going to talk about computationally robust compilation. We're going to restrict the context. We're going to restrict the attacker and the simulator to be these polynomial time contexts. And now we have the same thing we had on the UC side, right? We only care about polynomial attackers, and we require the simulator to be polynomial time. And we can also replace this equality with indistinguishable behavior, which sort of absorbs the polytime environment into it. Now, these are really simple changes I've made here. But I want to point out that they're also a fundamental extension to the robust compilation framework. The robust compilation framework doesn't really have a way to talk about this. And so we need to add one in to be able to make these sort of conceptually simple changes. But when we make them, we end up with a notion of computationally robust hyperproperty preservation. And I want to look at this just a little bit more technically, right? Robust RHC, the standard one, the one from the Journey Beyond Full Abstraction paper from a few years ago, it says that for all programs and all attackers, there exists a simulator such that these look the same, right? But we really fundamentally cannot put any restrictions into these holes. And to get computationally robust compilation, we have to put restrictions into those holes. So we're extending the framework to do this. And we make this change, and we made it to follow the process of UC security. And so the last step is to make sure that these changes actually did what we wanted, right? And indeed, we're able to prove that it does do what we want. We can get this theorem that says that computationally robust hyperproperty preservation corresponds precisely to computational UC emulation between the source and target programs for all possible programs. So part of me wanted to just end the talk here and say, hey, look, we did it, right? But I was told I was supposed to talk for about 17 minutes, and I don't think this has been anywhere close to 17 minutes. So there's a few other aspects of this that I want to get into. And the first one is about classifying preservation of hyperproperties. So I described robust hyperproperty preservation by saying the source and target programs had to have the same behavior. But there's another way to look at this that is, again, not new to us, right? This comes from the Journey Beyond Full Abstraction paper, to say that robust hyperproperty preservation is, as the name would suggest, preservation of all hyperproperties. What that means is that for any hyperproperty H, if the source program always, we have a source and target program, right? If the source program always has behavior in H, then the target program is also always going to have behavior in H. But what about the computationally bounded case? What does that look like? Well, at its core, computationally robust hyperproperty preservation is actually preserving computational emulation. So that means that for any functionality, right, this is sort of one of those ideal functionalities, for any functionality, if the source program emulates that functionality, then the target program also emulates that, computationally emulates that functionality. Now, this might sound like a statement of, this might not sound like a statement about preserving hyperproperties, but it kind of is. Because emulating F here means that all of your behavior looks indistinguishable from the behavior of F. So we can just take the set of behaviors that look indistinguishable from the behavior of F, that's a hyperproperty, and say that you're in that. Your behavior is in there somewhere, and that's a hyperproperty that we call CH. For, I think it's the computational emulation hyperproperty. And the computational here, though, this is not actually exactly about the hyperproperty specifically. We also need to restrict the class of contexts we look at the same way we did before. So this is actually going to put the same restriction. We're going to need the same extension to the framework that we had before to even state this computational requirement. But indeed, once we put all of that together, we get exactly what we were looking for, right? This CRHC thing I was talking about earlier is exactly the same as a polytime preservation of emulating every possible functionality. There's one last thing I want to say, which is in a somewhat different direction, and it's about generalizing this. So I never really defined polytime, and I barely defined computational indistinguishability for you. And you might have assumed that's because these have totally standard definitions and because I was trying to make things simple so that the talk would be understandable. And you're not wrong. But that's not the only reason I didn't define them. I actually didn't define them because fundamentally, for the math to work out here, the definitions don't matter. In fact, in the paper, we prove something considerably more general. And the first thing that we can do is we can replace these polynomial predicates with just arbitrary, uninterpreted predicates on programs. And we can do the same thing for indistinguishability. We can replace it with a totally arbitrary equivalence relation. And now we have a way more general property that we refer to as predicate robust hyperproperty preserving compilation. And the neat thing is, this generalization buys us quite a lot. It really works, right? And so what do I mean by it really works? Well, it represents a bunch of different stuff all at the same time. The simplest version is we can give a trivial predicate true. So this allows any program in any context to be considered. And we can demand full, complete behavioral equality. This devolves into exactly robust hyperproperty preservation. And we already know that corresponds to perfect UC security. We could also go in the other direction. We could demand that everything be polynomial time and only care about computational indistinguishability. And this pretty immediately devolves into computationally robust hyperproperty preservation, which we proved in this work is equivalent to computational UC security. That's cool. We've managed to catch both of these, but we do not have to stop there. We could, say, allow for arbitrary programs, but only demand indistinguishability. This doesn't correspond to any sort of robust compilation property I've already told you about, but it does correspond to a notion of UC that exists and that we understand, which is statistical UC security. This requires that the behaviors be statistically close to each other, but they don't have to be exactly identical. We could go even farther if we wanted to. There's a bit of a rabbit hole here, right? For instance, we could use sort of some weird equivalence that's very weird in this context, but not in other contexts. We could require the equality of behaviors when restricting to things that a certain security level. So this could essentially tracks whether or not secrets are leaking. It corresponds to an information flow style non-interference definition. I have no idea what kind of UC security this corresponds to. I would be shocked if it corresponded to anything that's already in the literature. But the thing that's really neat here is that this work gives us the language we need to start talking about that and to start investigating it and to really make these connections more broad and more deep all at the same time. So where are we, right? What have we done? Well, I told you about a generalization of the robust compilation framework to get this notion of predicate robustness. And I showed you how we can use this to define computationally robust hyperproperty preservation, and that corresponds precisely to computational UC security. And that this polynomially preserves this class of hyperproperties. All of the proofs are verified in Isabelle Hall. We have machine checks proofs for everything. There's also in the paper, we use this to support a UC proof of a model of the WireGuard protocol using CryptoVerif. And the full paper for this should be on my website as of a couple hours ago. I should probably check to make sure it deployed properly. And will be appearing at CSF this upcoming summer. And with that, I would be happy to take questions.
Questions?
Hi, cool stuff. You showed that we can go from the one direction to the other, and that we can generalize this. But hyperproperty preservation is just one of the many secure compilation criteria we already knew of. Do you know whether this also works if we go for something like relational hyperproperties or just anything else that we already know about?
The short answer is the generalization of the robust compilation framework should translate with no problem to those. Those, so far as I'm aware, do not correspond to a meaningful notion of security in the cryptography world that people use. This was actually a sort of an open question for quite a long time, is what is UC security, and all of these other sort of cryptographic definitions, what do they correspond to in the PL world? And we think the answer is, robust trace property preservation and robust relational hyperproperty preservation don't really seem to correspond to something that people use. But Marco's going to disagree with me. No. Yes, okay.
There's something worth adding here. It's that depending on the trace model, and the UC trace model is very funky. There's a lot of collapses. If you know the diagram from the journey beyond full abstraction, there's many points, there are many elements in that diagram. Now, it turns out if you start adding language features or constraints on the trace model, some of those things collapse. I don't remember these collapses by heart, though, with the UC trace model, but if I remember correctly, I think all the relational stuff gets squished down to RHC. But I don't remember. There's a long time ago.
Now that you mention this, I also remember there are different UC models, and in some of them, there's a quantifier ordering that I sort of had implicitly on my slides that is the classic UC quantifier ordering. And in some UC models, you can actually reorder some of those quantifiers and get things that look like they should mean very different things, but actually collapse. And it really depends on the model. There's a bunch of models floating around out there. Yeah.
We have time for one more, maybe two questions if it's brief.
So yeah, I wonder about this last point. Like, how did what you presented help you with this proof?
Yeah, that's a great question. Unfortunately, the right person to answer that question is Robert, who's not here today. But essentially, what it lets us do, so CryptoVerif is a tool that's designed for proving computational indistinguishability. And what this does is it gives us sort of a deeper understanding on the PL side of how computational indistinguishability relates to UC security, right? So using a tool that is sort of more of a formal verification tool designed for computational indistinguishability, making sure that that actually corresponds to a full UC proof is something that we didn't have the framework to really properly talk about what was definitely necessary before.
Interesting.
Yeah.
So maybe while the next speaker sets up, I can ask a final question.
Yes,
so
please.
Is there some way to instantiate your framework to get some kind of quantum resistant security? Or?
Ooh, that is a great question. I have not thought of that. My guess is that most of the computational model and the predicates are left fairly abstract. So my guess is that if we instantiated the computational model with a quantum computational model and the predicates with an appropriate notion of fast for the computational setting, it would be able to talk about that. But that's not something we've directly investigated, and I don't know what the ramifications would be.
Okay, so the next speaker is Haoja Sun. I tried to practice this and have probably failed.
You're good.
Who will tell us about gradual verification for smart contracts?
Hello. Hi, everyone. Good afternoon. My name is Haoja Sun, a senior undergraduate student from Shanghai Jiao Tong University. And I'm delighted to share our ongoing work with you about gradual verification for smart contracts. So this is joint work with Kunal, Jane Paul, and our advisors Jonathan Eldridge and Jenna Weiss. Great thanks to all of my collaborators. So first of all, I want to talk about why our work is of great importance. We all know that the smart contracts are self-executing programs on the blockchains, and they facilitate secure resource transactions among mutually untrusted parties. And therefore, if these contracts have vulnerabilities, it could result in significant financial losses. I'm sorry, I lost my mouse, I think. Just give me a second. Sorry about that. I think I lost my mouse. Okay, cool. Here it is.
We don't see your screen anymore.
Oops. Let me check. Sorry about that. So I just talked about the vulnerabilities, and it may cause the huge financial losses if there have bugs in the smart contracts. So actually, the three properties of smart contracts highlight the importance of the verification. So firstly, it is the immutability. Once the smart contract is deployed, it cannot be changed. And this means that the bugs in the smart contracts are irreversible. And secondly, transparency. The code and operations of all the smart contracts are visible to everyone. While fostering trust, if the errors are present, it becomes straightforward for others to identify the bugs and initiate the attacks. And thirdly, automatic execution. The smart contracts operate without human intervention when meeting predefined conditions. And if there are issues with the smart contracts, they might execute incorrect operations without notice. And thus, it's really critical to verify the smart contracts before the programmers deploy them on the blockchain platform. And nowadays, there are two mainstream verification methods, the static verification and the dynamic verification. For the static verification, even though it can provide strong guarantees, it burdens the developers by developing exhaustive and meticulous specifications. And let's look at this smart contract example, which is written in the PyTeal language on the Algorand blockchain platform. And the PyTeal language allows developers to write the smart contracts in a high level, and its syntax is similar to Python. And this example manages a list of 10 account balances and calculates the maximum balance. And in order to fully statically verify this piece of code, the developer needs to write the precondition and postcondition, requiring that the balances array is initialized and populated with non-negative integers. And for the for loop, the loop invariant is needed at the start of each iteration to ensure that the max balance must contain the maximum balance seen so far. And moreover, the process of updating max balance would use fold and unfold to reason about the parts of the array processed so far and the part that remains. And finally, a lemma would be used to prove that the maximum balance found is indeed the maximum of the entire array. And as we can see, the static verification has a large upfront specification cost. And besides, another disadvantage of static verification is that the unverified external code can break a contract's assumptions. The given example wants to handle the action of purchasing items. It calls another function in another smart contract to check whether the item is still available before each purchase. And in this case, this external contract may not be verified and may break the assumptions its caller makes. And since this behavior is undefined, it is difficult for the developers to write the complete and correct specifications. And on the other hand, for the dynamic verification, even though the techniques offer flexibility and ease of use, they can only uncover vulnerabilities in executed program paths at runtime. And also, they might increase the runtime overhead for weaker assurances. And besides, the runtime checks incur substantial transaction fees on the blockchains, increasing the monetary cost of executing the smart contracts. Fortunately, the Grady verification allows developers to incrementally build up correctness specifications and proofs. And thus, the developers can focus on specifying and verifying the most important properties of their smart contracts. And the immediate verification feedback is a significant advantage of this approach. The Grady verification supports static verification where possible and dynamic verification where necessary. And Grady verification introduces a concept called imprecise specifications, marked symbolically as question marks. And these serve as placeholders. They represent unknown parts of a specification or combined with the known parts. And the verifier treats these imprecise specifications optimistically, but inserts the dynamic checks where necessary to maintain the soundness. The core of the Grady verification is founded on separation logic, a form of logic that enables modular reasoning. And the simple explanation is that we can view the AND operator here as a separation conjunction. And the Grady verification systems have three properties. The first one is soundness. Simply, if the verifier tells us it is correct, the static verification passes and dynamic checks do not fail, then the program is correct. And to elaborate on this topic, we could read Conrad's paper, which was presented yesterday. And the second property is gradual guarantee, which ensures that relaxing specifications should not introduce new static or dynamic verification errors. And the third one is a conservative extension, which says that anything provable in the base static system should be provable in the gradual one. Since our graduate verifier extends the base static verifier syntactically with graduate formulas, our system assumes non-contradictory strengthening of imprecise formulas. And thus, I will discuss the three significance of graduate verification in the context of smart contracts. So firstly, the graduate verification provides the balance between precision and flexibility. The developers start by writing partial specifications, providing the freedom to progressively strengthen these specifications over time. And moreover, the programmers can specify only the components they care about in smart contracts. Back to the previous example. If the programmers only care about whether the program's output is correct, they can only specify the preconditions and postconditions and add question marks in the loop invariants. And after the program passes the verifier, they can then further complete the verification by specifying the loop invariants and other parts like fold and unfold and the lemmas. And secondly, on the dynamic side, graduate verification can help reduce runtime overhead. The transaction fees and computational resources required for executing smart contracts can accumulate quickly, like the Ethereum gas fee, which increases with dynamic verification alone. And graduate verification minimizes this cost by minimizing runtime checks with statically available information. For example, in this simple code snippet, where we want to subtract a number quantity from the count value, we need to have 5 asserts with the dynamic verification alone. However, when we statically verify some of the properties, the number of the asserts is reduced. And when a proof obligation has been fully statically verified, no runtime check is generated for it. And therefore, the developers may choose to spend more time incrementally specifying their software to reduce the dynamic checking overhead. And finally, graduate verification can protect against unverified code and reentrancy. When interacting with unverified external code, graduate verification can insert dynamic checks. And these checks prevent type violations and unauthorized access to memory, which unverified code might otherwise exploit. And reentrancy attacks are a major concern in smart contracts. And these attacks will occur when a function calls an external untrusted contract. And the untrusted contract can then call back into the original contract. And this can potentially disrupt the state of the original contract. Graduate verification can mitigate such attacks by specifying the state invariants that must hold before and after the external calls. And graduate verification can ensure that the contract state remains consistent even if reentrant calls occur. And next, I will discuss our graduate PyTeal framework, which is used to gradually verify smart contracts on the Algorand blockchain platform. And the smart contracts are written in a language called Teal. It is an assembly-like language, and it is processed by the Algorand virtual machine, AVM. And PyTeal is another language that allows developers to express smart contract logic purely using Python syntax. It is high-level, and since the Teal is low-level and complicated to write specifications, we choose PyTeal as our target language to develop the graduate verification framework. And our model can be divided into 2 parts, the front end and the back end. In the front end, we convert the PyTeal programs to graduate CNOD, the only previously implemented graduate verifier. And internally, graduate CNOD uses a variant of the Viper toolchain to statically verify functions, treating partial specifications optimistically. And then, the modified Viper backend generates the runtime checks wherever static verification cannot assure specifications. And these runtime checks are added to the original smart contract before compilation to the Algorand platform. And to be more specific, we construct a parser using the FastParse Scala library to parse the PyTeal source code with specifications into an unresolved PyTeal abstract syntax tree. And since Python supports the dynamic typing, but we're translating to a typed intermediate language, CNOD, we use type inference to assign the static types to all variables in the PyTeal AST, resulting in an unresolved PyTeal AST with inferred types. And we perform type checking and other well-formed checks, then translate the resolved AST to CNOD. And the CNOD AST makes some operations more explicit, aiding some verification and connecting to the intermediate representation supported by graduate CNOD. And during the static verification, the verifier optimistically interprets the imprecise formulas to satisfy a contract and denoted by the question marks. And this will be caused by the optimistic static verifier. And when those optimistic static verifiers succeeds, a set of runtime checks are produced that must be executed at runtime for soundness. And we then identify the locations when the runtime checks should be inserted based on the placement of the question marks embedded in our PyTorch specifications. And we develop the Weaver module to perform the step and encode the checks in the original PyTorch program at the identified locations. And finally, the PyTorch program with the runtime checks is transformed into an executable contract within the PyTorch compiler, which is subsequently executed on the Algorand platform. And next, I will walk you through an example for gradual verification of smart contracts through the incremental improvement of specifications. And this piece of code depicts a selling transaction where a specified quantity is subtracted from a global state variable count. And it will start with the most imprecise form and then gradually refining them. Initially, we can place cross remarks in the contract specifications to indicate maximum imprecision. Assume that we only know our argument quantity should be more than or equal to 0, but we know nothing else about the preconditions and postconditions. And after we run the program, we will know that some dynamic checks will be inserted. For example, it will check the accessibility predicate to see if the program has the ownership of the count space. And since our verification is based on a resource logic, and so the predicates have to declare what global state they use. An accessibility predicate is a logical construct used in separation logic, which asserts that a specific memory location is accessible, enabling the modular reasoning about the state of that memory in a program. And then, before decrementing count, it will check if the count is sufficient to cover the quantity. This is to prevent underflow in a subtraction operation. And finally, after decrementing, it will check if the counts remain non-negative. And this is a standard check after an arithmetic operation that could potentially result in a negative value. And for the second step, we can elaborate our specifications and then reduce the dynamic checks. And finally, we could complete our specifications to pass the static verification and no dynamic check is inserted. And in conclusion, we talk about the significance of gradual verification for smart contracts. We talk about our current gradual PyTorch framework, and we talk about the incremental gradual verification smart contract example. But our journey doesn't end here. Looking forward, our primary objective is to transition from the CNOT verifier to the independent verifier for smart contracts. And our next goal is to enhance the verification for smart contracts that involve external costs. And additionally, we plan to expand our set of runtime checks, specifically for the smart contracts. And finally, we're setting our sights on the ambitious goal of verifying smart contracts at the byte level. This is the end of my presentations. I'm happy to take any questions. Thank you.
Hi, thanks for the talk. I was wondering if how does your verification intersect with the gas metering? Like, is there anything specific you need to do? Can you do assumptions about gas consumption?
Yeah, so actually for the current step, our prototype doesn't support the estimation of the gas fee, but we know that in the specific context of the smart contracts, the gas fee is really important because when we execute the program on the blockchain platform, we need to pay the fees, the gas fees. So that in our future work, we want to include the estimation of the potential gas fee included to verify the smart contracts on the blockchain platform. So it is included in our future work.
Okay, thanks.
Other questions?
I'm wondering a bit about the first point here. Maybe you have said some things during the talk, but what are the advantages you gain by moving away from the CNOT verifier?
Yeah, so actually there are like three main reasons. The first reason is that right now we are like translating the PyTorch language into CNOT. And CNOT is like a static type language, and PyTorch is similar in syntax in Python. So we need to do the type inference. This is the first reason. And the second is that because I mentioned the global state, that is the heap locations that we need to check in our gradual verification system. But right now we need to manually translate the global state in PyTorch into the structs, the data structure structs in the CNOT. And this is like another disadvantage for the CNOT gradual verifier. And also I mentioned, for example, the security permission. Like if we call the external contracts in our current smart contracts and we don't know the implementations of the external contract, we need to check the state invariant, for example, like what states are held or are keep consistent in before and after calling the external contract. And this isn't supported in the CNOT graduate verifier. So we want to elaborate on this to include more specific implementations of the security permissions with regards to smart contracts. And this is the second reason. And the third reason is that for the gas fee, because right now graduate CNOT doesn't have anything related to the estimation of the transaction fee, but like it is important with regards to dynamic checks on smart contracts. So we want to include this in our future work. Yep.
I have a question. So what kind of invariants has one to write to prevent reentrancy?
So for example, like the state invariance, and secondly, for example, the resource ownership. Like when we do the transactions in the smart contracts, there might be something changed before and after we call the external calls. And in that case, some states might be, some states should be unchanged and some states should change within our within our requirements, so that we can explicitly specify the state invariance and the resource ownership in our specifications to verify the smart contracts.
Actually, related to that, can those be statically checked? Like reentrancy invariants can only be dynamic, can they?
Yeah, so the reentrancy calls include some of the recursive calls in the smart contracts, and I do think for some of the state invariants, if we design carefully, I think some of them might be statically verified, but I'm still not sure because it isn't implemented in our current work. But I do think we need to consider that in our future work, yeah. So maybe the dynamic checks are only considered with regards to the reentrant calls.
Yeah, because I'm thinking you have a contract that does a callback that is perhaps not even verified. It's outer code, so you have no way of knowing that piece of code is not going to re-enter back. At that point, when you're verifying the contract, you need to insert a dynamic check because you don't have the other code, right? So
exactly.
Yeah.
Because for the reentrant calls, because we don't know the implementations of the external calls, so that you think that we cannot statically verify that because we don't know the implementations, but we can specify some of the state invariants. For example, before and after the calls, some states might be unchanged and some states might be changed according to our requirements, right? So that we can specify them in our static verification framework.
Cool. Okay, looking forward to seeing more of this.
Thanks.
I had a question myself. So there was a talk at POPL about, if I remember correctly, soundness of CNOT.
Yeah, exactly.
Is there any hope of using that to get provably sound, provably safe, or provably correct smart contracts?
Yeah, of course. So actually, what we're using now is the graduate CNOT, as you indicated in the presentation yesterday. So we use the exact same base graduate verifier. And based on this CNOT graduate verifier, we built our own graduate POPL'24 framework. So actually, we need to further guarantee our graduate POPL'24 framework, but it is based on the graduate CNOT, just as depicted in the presentation yesterday. Yep.
Thank you. So with that, I think we should pass the floor to Gregory. Maybe if there's a final question while Gregory sets up.
So I was wondering what happens when on-time assertions fail. Do you always just stop, or do you attempt to make sure there's some kind of liveness to these contracts?
So you mean for the dynamic or the static verification?
The dynamic checks.
Yeah, so actually we're compiling them through the TIL compiler, and after that we run the smart contracts on the Algorand platform, and if there are dynamic checks failed, there will be an error message pop out.
Yeah, does that mean that resources can get stuck if you have some money in a contract and then you can continually fail the contract? It might never get out.
I think like right now we haven't tested, but yeah, I think this is like a potential problem that we need to consider in our future work.
Okay, thanks.
Thank you.
Okay, and with that, it's time for the final talk of this year's PriSC, someone we have already seen today. So I guess I don't have to introduce you again. So let me immediately give you the floor.
Thank you. This is the title with, or the, sorry, this is the talk with a longer title, towards a modular specification and verification of a concurrent hypervisor-based isolation. So this is a little bit odd as the second talk, but I talked about our virtualization platform. And this is what it looks like kind of at the implementation level. I mentioned it was this microkernel. And so that's this Nova piece. Nova is this microkernel. And on top of the microkernel, we run a variety of applications, a virtual switch, the VMM application that we talked a lot about in the last talk, this UMX, the console multiplexer, and this master controller. And there's this interesting thing up here with this customer services that could be people running other processes which have not been verified on top of this microkernel. And our big ambitious goal, as I mentioned in the last talk, is to verify this stack against a strong user space specification. And that specification might be something like runs these virtual machines correctly or something like that. The focus of this talk, unlike the last talk, this talk is going to be about Nova. And in particular, how do we draw this, like what is the formal representation of this black dashed line? And how do we prove things on top of it? So to set that up, I have to tell you a little bit about what Nova is. So Nova is this microkernel. And it exposes 15 or 16 hypercalls. I believe there's 16 possible, and one is reserved for future use. It basically divides the system up into a bunch of different resources. This is kind of what it looks like at the hardware implementation level. The blue components here are reflected into user space. Okay? So one thing that's different from commodity operating systems is that devices, all device drivers are written in user space. And we'll have to find a way to reason about user space applications that are driving devices. Memory is obviously accessible, but things like page tables, this memory controller and SMMU, for example, are privileged and therefore controlled exclusively by Nova. So the API has 5 kernel objects. This is a capability-based microkernel. It's got protection domains, which mean basically address spaces, which include both memory and objects, pointers to other objects. It's got threads, which are made up of ECs and SCs, portals, which are a means of doing inter-process communication, and semaphores. And for the purpose of this talk, the most understandable of these things is semaphores, so I will talk about that one. But before we go into that, let's talk a little bit about where we're going to go in this talk. So I told you a little bit about the implementation. It's written in C++ in assembly. That adds its own level of complexity. But I'm mostly going to focus about the specification and how we express that in separation logic. Then I'm going to talk about 3 different things we're aiming to prove on top of that specification. One is going to be verification of user space applications, so we know that the whole system does something useful. Generally, the interesting thing about operating systems don't do anything useful to people outside of the computer, and that's kind of nice. So we're thinking about, running a web server on Nova means your computer will act like a web server. We're going to think about robust safety, showing that Nova is protected from user space applications, no matter what user space applications you run. And we're also going to think about those situations I mentioned before, which is where some of your applications are trusted and some of them are not, and establishing robust safety of trusted applications or verified applications against unverified applications, and see how we can do some of those proofs on top of this and speculate on how we can do more of them. All right, so this is what the Nova specification looks like. It is not 12,000 pages, thankfully. It's only about 100 pages or so, I think. This is control SM, which is the thing that does semaphore up and down. And the way we express this in separation logic is we build so we say there's 2 pieces of ghost state attached to every semaphore. Every semaphore has a value, and it has a list of waiting threads. Okay, and so we express those in separation logic by this SM value. G here is going to be the name of the semaphore. So SM value G0 says the value of the semaphore named G is 0. And SMQ GLS means that LS, the empty list, says no one's waiting for the semaphore. And then to specify what does control SM do, like for up or down, this is what it says. So this is written in predicate transformer style. We say the weakest precondition of the hypercall of control SM with doing an up is first take the number, because we can't have pointers in this model, because pointers into the kernel would obviously be very bad. So instead what we do is we take a number that's local to our protection domain, and we resolve that to an object. Now that object might have the correct or adequate permissions, or it might not. If it doesn't have adequate permissions, we'll just stop. We'll immediately return bad cap, I think is what the error is called. But if we do succeed, then we'll use SM inker to atomically, using an iris atomic update, to atomically increment the value of SM value. So it'll go from v to v plus 1. For the purpose of presentation, I'm ignoring the potential overflow there. So the idea here, the takeaway message from this is that when you want to specify a hypercall like this, or when you want to specify functions like this, they're generally commit in multiple steps. So we can't just do it like a hypercall commits in many steps, potentially very many. And you also need features like non-deterministic choice and things like that. And all of those ideas are easily expressed using separation logic assertion, so we can give nice predicate transformer semantics to them. I should say that a lot of things I talk about are just the specs. This spec is actually proven. We've actually verified C++ code inside of Nova that does all of this. It proves this specification of the control SM. It calls functions that are only specified for things like scheduling, but all of the logic around SM up and SM down is all verified within Nova right now. All right, so we need to take that, that WP hypercall and kind of plug it into and use it to describe the semantics of user space. And we do that via this axiom, or via this definition, WP Nova EC. That's going to be the weakest precondition of a thread running in Nova in user space. And we can think of it as that thread has some register state, and Peter and I had a long discussion in the break about what is the register state of Nova, of an application running on top of Nova. But for most of you, you could just think of it as registers. And that thing's going to take a step, possibly emitting an event. That event might be a hypercall. I need to do a hypercall. And so then we'll just dispatch this WP hypercall. And then when that hypercall returns, we'll end up going back and resuming the execution of that user space thread with updated register states. All right. And this is posed as the axiom that we give in Nova that tells you how all these things work. But this WP Nova EC actually is given a definition inside of Nova. And the theorem that we prove at the beginning of Nova when you start up is something that looks like this. It says you give Nova all the resources of the machine, so all the memory resources, all the device resources, all that. It consumes all of those down here. You also give it kind of ownership of the execution of the CPU. And you also tell it you can kind of behave like this. Right, so this is what user space is going to do. There's that WP Nova EC. So what's above that, what's above right here, this is all the resources that are given back to the user. So Nova's wrapping them up, re-exposing the raw resources as Nova resources. All right, so that's the specification that we're going to give to Nova. We aim to prove that using a variety of great proof techniques and axioms about C++ and whatnot. So now let's talk a little bit about how we might take that proof and build interesting verifications on top of it. So if we imagine that when we boot up, when you push the power button on your machine, you might start like this. There's your CPU running over here, and you have to behave like that. And then you've got all your physical state. You're probably the only one running at that point, though in reality, there's so many things that run before you, it's ridiculous. And you want to act like the spec init thing. And we think about this using a technique from a very long time ago called carousel, which basically says that if you prove something like this, set up in an appropriate sort of way, you can use iris adequacy, iris didn't exist at the time, to extract a proof of operational refinement between these two things, as long as you make sure that spec init is adequately connected to the operational semantics of the underlying machine. And then using this theorem. So that's what we want to prove. And if we can prove that, we'll be able to get this nice refinement property. We can apply that theorem nova OK that I just said. And that won't mess with the left-hand side of this entailment because we have framing and separation logic. But we'll use that and we'll get out, we'll forget about the raw resources and we'll end up with the nova resources. OK? And then I can take that and using some assumptions about C++, I can review the fact that I've loaded a program that just happens to be the compilation of a C++ program in memory. And I can kind of think about that as being like, well, let's think about those bytes instead of being actual bytes as being some program in memory. And then I can prove spec init entails that C++ program. So that basically says, if I prove my program correct against this carousel style specification, I'll be able to compose that with the C++ axiom and the nova proof and ultimately extract out this adequacy theorem. So that's the way that we aim to verify interesting properties of this whole system that's built by this stack. All right, so now let's talk a little bit about robust safety. So you recall that in the nova specification, we had to quantify over all startup images, OK? So that seems like it's pretty good, but we also gave you this kind of weird thing, and it's not entirely obvious that this is provable. Like maybe WP nova EC is just false, and it's very easy then to prove this theorem. And nova just becomes unusable. But if we can show that this assumption is provable for any startup image, whether it's good or bad, then we'll basically be showing that nova is usable. And the way we aim to do that is by constructing, well, we need to prove this, that those user space, so we're gonna construct an iris invariant here. We're gonna need to show that those user space invariants are sufficient to build that iris invariant, RSInv here. And we'll show that RSInv is sufficient to prove that WP nova EC appropriately. And you can see basically what we're doing here. We are taking all the state we own, and we're existentially quantifying over the V's and the lists of execution contexts. So we are not going to be able to say anything using this invariant. We're not going to be able to say anything about the value of the semaphore. But we're going to be able to say there is a semaphore. And because of the setup of our specifications, the fact that there is a semaphore is enough to justify that I can take a step. So it would be enough to prove this theorem. And mainly this bottom one that says that WP nova EC is provable using just RSInv. All right, so now on to the last of these, which is kind of interesting, where we have hybrid clients, and we have verified and unverified code working together. So here's the example. Nova is kind of like a very low-level thing, and a lot of people want to program in something that's not quite as low-level. In the Bedrock stack, we have a master controller that runs on top of Nova, and then user space applications talk to that. And what we see is that the master controller is usually the one that's communicating with Nova, like saying, create me a semaphore. And when the master controller asks for a semaphore, it's going to get exact ownership of that. It's going to know the value of that semaphore is currently 0, and there's no one waiting on it. And that's important so that he can put his own policy on it. Maybe he's going to use it as a synchronization primitive or something like that. But he also wants to be able to give that semaphore potentially to unverified code. And then he has to carve up some protocol that describes that will be robust against this guy. So he knows that no matter what this guy does, he can't violate that protocol. All right, I'm just about done. And that can be achieved in separation logic by carving out a slightly smarter invariant. So for example, if the master controller wants to give shared ownership of a semaphore to this unverified code, but say he only gives up permissions. He says, you can up the semaphore, but you can't down it. Then he can easily carve out an iris invariant for just that semaphore that maybe has a lower bound. So he says, I don't know how many times this guy might up it. Maybe he'll never up it. Maybe he'll up it a lot. But I know that if I don't down it, the value will be at least 3, for example. I don't know what that thing might be. So he'll be able to make assertions about portions of the state in interesting sorts of ways. And we've done some experiments about how we can both give state out and also revoke it. Revoking is much more difficult because you kind of have to show that his capability space, he couldn't have tucked that semaphore anywhere that you didn't know about. And the way that's handled in our setup is the master controller can track everywhere where this guy puts that capability. So he can go in, and the master controller can remove all of those ways that he has to access that. And after he removes the last one, he can kind of show, OK, there's nothing that guy could have done, so I can kind of take that state out of the invariant and have a hold on it sequentially now. All right, so that's it. Right, so I told you a little bit about what Nova is, how it works, but mainly how it's specified. We've got this WP of user space threads in Nova. Then I told you how we have done many system verifications on top of that. We, for example, verified a user space synchronization library with semaphores and reader-writer locks and things like that on top of the Nova specification. So that's verified in C++. The C++ library that runs in user space is verified on top of the Nova specification. Told you how we aim to prove robust safety. That's not a completed proof, but we've done some sketches of it, and we believe that is very tractable. And we have done some additional actual proofs of hybrid clients, kind of establishing some of these smaller invariants. But we have not done a revocation proof at this point. And we think that would actually be very interesting, but we'll have to wait for the next time. So that's all I have. Thank you very much.
Questions?
John?
I am kind of curious about the claim that robust safety is tractable. I mean, because you need to kind of inspect all instructions of the machine and make sure that none of them does something that allows privilege escalation. So how do you manage to do that for a large architecture?
That's a good question. That's an excellent question, actually. And that builds off the contents of the last talk. So the idea is that one of the bits of unprivileged state is going to be basically the register file of each thread. So that's completely unknown. But we know that machines don't actually get stuck, or we assume machines don't actually get stuck. So there's always a transition that can be taken from any register state, and it will emit one such event. And the number of events that we have is relatively small. Does that make sense? So basically we're saying it doesn't matter at all if the user space application is incrementing this register or whatnot. All we have to think about is when it starts interacting with the outside world, or sorry, not the outside world, with coming out of the CPU, out of the unprivileged piece. So that's going to be making a system call, accessing memory, taking a fault. All of those things involve the rest of the machine, and we'll have to prove that all of those preserve that invariant. And basically, it would be thinking about this. It would be the interesting part will be case analysis on the event. So we know one of those events will happen. And we have to show that all of the branches of that match preserve that invariant. Does that make sense? OK.
I guess a timer interrupt is also one of the events that can happen.
Timer interrupts are actually not exposed to user space. So what happens, timer interrupts are fully absorbed within Nova, and that's captured by the fact that we could have multiple threads running WP Nova EC, and Nova can pick which one, kind of like cooperative, but not really cooperative threading. But device interrupts are actually also owned by Nova, but Nova accepts the device interrupt, ups a semaphore, and then does not actually pass it on to a thread. So the way that a thread would wait for an interrupt would be to wait on a semaphore. That's how interrupts are exposed to user space.
Other questions? Okay. Can I ask about like you talk about system verifications and you mentioned some libraries. Do you also intend to verify like full systems that involve some user space application where you want to prove some end-to-end property about, I don't know, interaction with peripherals or whatever, and on for that application running on top of Nova and
Yeah, So we have verified several applications up there, or we are in the process of verifying some of these applications. So we've verified device drivers that talk to devices and drive, for example, serial ports and stuff like that. The UMX here is a verified application. It's a console multiplexer. So if you type, you could say, I want to talk to VM number 3, and it will properly route your bytes to that VM. It doesn't say anything about what that VM is going to do with it, but it does tell you that that VM will get this stuff. We've also, one of the things we're working on and we're nearing completion on is this V-switch, which is kind of like that console multiplexer, but it acts like a switch. So it's like an Ethernet switch. All of your CPUs or all of your guests are connected to it by VirtIO, and it will do packet exchange. So you can send a packet to Dominic or anyone else.
And since you're using Iris, I expect the kind of adequacy you get is then just like safety properties or what?
Yeah, we're just focused on safety properties.
Not confidentiality, not liveness.
Not confidentiality and not liveness, yes. Liveness we aren't too worried about. Confidentiality I think people would be very interested in, but I think, at least I'm not aware, maybe other people in the community are, good ways to actually say that, especially in the presence of things like timing channels and a lot of non-determinism that exists inside of Nova. That's can be difficult to reason about.
You can always over-approximate confidentiality as a safety property through taint tracking, right? So if you're fine with an over-approximation of confidentiality, I should be good.
We will get a notion of isolation.
Oh, right. Sorry, there was a notion of confidentiality specifically for robust safety in the paper from like 2007. Does anybody remember the name? So like, with respect to like confidentiality with respect to something like a fresh value. I forgot the name.
I'm not sure. Sorry. Oh, I was saying we are interested in isolation properties, and we the same sort of thing I mentioned about revocation is this sort of thing you would see for an isolation property.
Maybe a last question by Amin?
Yes. Maybe a stupid question. You said that you're doing refinement, but it was not clear to me what is the other side of refinement? What are you refining?
The specification?
Yeah.
Is that what you're asking? So in this case, it's probably better in the previous talk. So yeah, in the standard use of like download the Nova, download the Bedrock stack and run this, spec init would be the specification of what it means to run your guest code. So it's like you would say, I want to run this Linux live CD or something like that on the Bedrock stack.
Right.
The specification you would get is that we behave in a way that you could also see if you just put that CD into your, people don't really use CDs anymore, but USB stick into your computer and booted Linux off of that, where there's no hypervisor, right? So we're basically proving that the Bedrock stack doesn't exist in that case. Like it's as if it doesn't exist. We're not adding any new bad behaviors to the system.
Right.
But then we have other features in the stack that you can enable that would allow you to introspect and do antivirus or things like that inside, from the outside, but applying to the guest. So protect the guest from kernel corruptions or something like that.
So does it make sense that you quantify over all guests basically, or what in your theorem?
Yeah. You would quantify over all guests.
Yeah. Okay. All right. Thanks.
Yeah.
Okay, so I think I should pass the floor to Shweta now.
So we'll be concluding the workshop. I will keep it brief because people are very, very tired after a week of POPL. So firstly, I would like to thank Marco, my workshop co-chair. Also all the session chairs, Marco, Matteo, Dominique, thanks for running the show while I just enjoyed the talks. And then finally, all of you audience, you've been quite engaging. I appreciate that you took the time to ask the questions, and I hope all of you submit your upcoming works to the next year's workshop. And if you have any feedback, be it about topics and so on, please feel free to write to either me or Marco. We'll be happy to integrate your feedback. And with that, I wish you safe travels back and have a productive year ahead.